I have. Okay, so I started it, and as long as nobody stops it, it should just all work. And if at the top left it says recording, if that for some reason goes away, just press record again. But as long as nobody presses stop, that shouldn't happen.
Right, thanks. Okay, so far so good. Now if I switch to the toolbox, you can see the toolbox, right? Should I increase the font size of the toolbox for screen sharing?
On my screen, it could be a little bit bigger.
Yeah.
Maybe 1 or 2.
Do that.
I think Control Shift Plus should be shortcut.
Ah, okay.
Just in the editor, or just Control Plus. Depends on your keyboard layout, actually.
Yep. Thanks. It's good to have the developer online.
Okay.
So I'm going to another room where another workshop is running. Therefore, I disconnect from audio. But if you need any help, just send me a message on chat.
Thank you very much.
Or on Solib also works.
Sure. Thanks.
Okay.
It's fine. Yeah, Stephan, I realized that I got my time conversion wrong. So our session is directly before my Microsoft training here, so I have to leave kind of like sharp.
Right. You mean at the end of the
Yeah, right.
chat? Yeah, well, just disappear right when you need to.
Yeah, exactly. We just wave goodbye and then drop out.
Exactly. It's great to have you so soon. I didn't think that you were here already at this hour of the day.
Like I said, I got my time conversion wrong.
So I guess we're waiting for Igor to show up. Yeah, there he is. Sorry, Markus.
Hey, Igor.
Hey, Igor.
Sorry, I'm a bit late.
You want to test sharing your screen and so on?
Yep, I can do that. See.
Okay, I'll make you a co-host as well.
Igor, I thought you would, you're an Emacs user. Why do you have a Vim shortcut behind you?
I'm a Vim user. Why did you have this idea that I'm an Emacs user?
I don't know. I thought you were... Oh, I see.
Is it working?
Yep.
Yeah.
Perfect. Stop sharing. No, I mean, I also used Emacs, but
Okay. Yeah, maybe that's why it came up in an email.
I know how to run it.
I guess with Vim, you know how to get out of it.
Control X, Control C. It's a muscle memory.
Right.
You also want me to upload your slides to the web page?
I mean, yeah, I mean, I can give you PDFs. It's just the keynote. It has animations, you know, these recordings of the terminal, and that's like 100 megabytes, I guess, or something. I'm not sure you want to upload that.
I mean, it's GitHub. I don't know if they care. Might be above the limit.
I'm sure.
We could probably use GitLFS or just upload it elsewhere on the in-real machine, for example. But then I guess half of the world wouldn't be able to watch it anyway, right? Because
yeah, if it's keynote, I mean, the PDF is not. I'm not sure how useful it is without. I mean, you can use it without this stuff. Yeah.
Yeah, I will just upload the perhaps the PDF, then people get an idea. And
yes,
if they care enough, they can still ask you to get the
exactly.
big one.
I can also give you a link to a longer version of this talk, right? Because I just recorded it yesterday as a seminar, essentially. And
yeah, if you just send me there's room on the website. If you send me the links and whatever you want to have uploaded, I can do that. You also want me to send an updated version of the PDF, or is that the one from yesterday?
I'll send you a fresh version.
Hi, Matti. Great to see you.
Hi. You're looking great. So you're supposed to start in 14 minutes or so?
Yeah, a quarter of an hour or so, yeah.
Okay, yeah, very nice. So I see that you remember to record. So this should be the main technical obstacle this
actually,
year.
Fabian did that for us.
Fabian the Great.
Yep.
This is his new surname. Okay, but I see that you are the host. So
right.
Let me double check. Yes, Stephan Merz is the host. Okay,
yeah.
Good.
You want to be co-host or?
No, I'm going to
disappear to another.
Not to completely disappear, but to beam myself to other workshops. So I'm going to like robbing everybody all the time. So good luck and enjoy it, and very good job as always.
Thanks, Timothy.
Okay, ciao.
See ya.
Yeah, we had a lot of fun setting up this Zoom last week at Strangeloop with in-room Zoom, and then we had an echo, and at the end I thought I think the AV people got like 3 or 4 different computers to make this work. I felt a little bit bad at the end, but it worked.
But the recording is actually quite good. I mean, that's the team is doing a good job, right? The AV team. That's
Yeah. But yeah, I mean, I would prefer not to do a hybrid conference again. In person, it's easier and it's also nicer.
Yeah.
Every time before an in-person talk, I was like, oh, is the technology going to crash? I'm happy to see if the remote speaker was actually there. Yeah, but for the limited budget we had, it went quite well.
Hello.
Hi, Johannes.
How are you?
I see you.
Good. Thank you.
Yeah, Markus, I have sent you the link, the link to the PDF and extended version. Who's going to answer the Pascal question?
No, we don't have to use all of these questions, right?
Yes. Okay, so I put it in the bottom.
So I guess it is officially 2:30 in Freiburg, so we can probably start. So welcome everybody. It's great to see so many people interested in TLA+. So this afternoon, or whatever time of the day it is at your place, we are going to tell you a little bit about the specification language TLA+, and also about the tools that support it. So I have the pleasure to host this tutorial together with Igor Konnov from Informal Systems in Vienna and Markus Kuppe from Microsoft in Seattle, Redmond. And the schedule will be that I am going to start and introduce the language and basic tool support, and then we'll take a short break. And then Igor will talk about symbolic model checking in Apalache, which is a newer tool for verifying TLA+ specifications. And then I'll come back for talking about proof support for TLA+ in the TLA+ proof system. And at the end, all three of us will join for what we call the Fireside chat, basically to take your questions and just have an open discussion about why you're interested in TLA+ and so on. Also, if you have any question while we go, please go ahead and ask, either just ask on Zoom or post a message in the chat. I should be able to see your chat messages. Okay, so let's get started. So as you probably know, TLA+ is not our brainchild. It was designed by Leslie Lamport in the 1990s, let's say, essentially as a language to describe distributed algorithms, the algorithms that he was designing. And it was not really meant to be supported by tools. So Leslie likes to tell this anecdote of Yuan Yu, who wrote the first set of TLA tools, basically doing that against his advice. But then he convinced Leslie that actually that was useful. And so the tools grew from that date until today. So anyway, the language is meant to model and verify software-intensive systems, computer systems, whatever, in particular distributed and concurrent systems. And there are many languages to do that. One specificity of TLA+ is that it is a very logic-oriented language. So its logical foundations are mathematical set theory. So remember that Leslie Lamport is a trained mathematician. So he used set theory as a mathematician would do. And then he added a bit of temporal logic, and we'll see why. There is a web page, so if you Google for it, you'll easily find it with many resources. And if you want to have a good introduction to TLA+, I recommend the series of video lectures by Leslie Lamport. There's also this book, Specifying Systems, whose cover you see on the left of the screen. So you can download it also from the web page. It is a kind of reference language. There have been a few errata and so on since it was published, but essentially it is still the reference. A more tutorial introduction is a book by Hillel Wayne called Practical TLA+, with an accompanying website on learntla.com. So that introduction focuses on the Pascal algorithm language that we will not touch upon in this tutorial. However, we will show you most of the tools except for the Pascal translator that are supporting TLA+, in particular the TLC model checker, the Apalache symbolic model checker, and the TLA+ proof system. These tools generally are available from the TLA+ toolbox, and some of them also from the TLA+ VS Code extension, which has the advantage that you don't have to install anything but can just run it from the web. However, for this tutorial, I'll use the toolbox because its functionality is a bit more complete. Okay, so what we'll do here is I'll introduce basic concepts of TLA+. However, I will not go into details of syntax and so on. I hope that you will be able to read what you see on the screen. If you have any questions, then please let me know, please ask. I mean, it's supposed to be interactive. But I'm going to focus more on the foundational concepts, that, let's say, of the language. I'll give you a glimpse on how to model systems in TLA+. And in particular, I'll show you an example of an algorithm for distributed termination detection. After all, this is a satellite of DISC, so a distributed algorithm conference. So I thought I'd take a well-known distributed algorithm. And as I said, I show you some of the support tools. Okay, so let's go ahead. I'll show you the algorithm that we are going to look at in this tutorial. So as I said, it's about distributed termination detection. And so we suppose that we have nodes arranged on a ring. So here in this picture, I have 4 nodes that sit on a ring. Note that they are numbered counterclockwise. That will be of importance later on. I mean, it doesn't really matter, but that's the way the algorithm is set up. And these nodes perform some local computation that we don't really care about, and then they may terminate, locally terminate. And now the purpose of termination detection is for the node 0 that plays a kind of special role and a kind of master node to detect if and when all the nodes have terminated, so have become inactive. So in my pictures, I'll draw a double circle like here when a node is active, so when it's performing some computation, and a single circle like here when the node has become inactive. Okay, so how can you solve that problem? So we assume that the master node has no direct access to the local state of the other nodes. So there has to be some communication. And what we are going to do is we'll send around a token. So initially, say the token is at the master node, and it's just sitting there. And during the algorithm, whenever a node stops being active, so when a node has terminated, then the token will be passed around to the neighbor node. And here we go clockwise. So when node 0 terminates, like here, you see node 0 has terminated, then the token moves on to its neighbor. So now it's sitting at node 3. And after a while, node 3 may terminate, and it will go on to node 2 and so on. And in the end, it will come back to the master node. And so then the master can declare that all nodes must have terminated. Simple, right? Well, actually it is, but it is also a little boring because here we are just considering local activity of the nodes without any interaction, without any communication between the nodes, except for passing the token around. So let's spice up things a little bit. And let's assume that nodes may send messages. And so, for example, what can happen like here is that node 2, which is still active, sends a message to node 3 that had already terminated, right? And when a node receives a message, even if it has terminated, it will become active again. So this message reactivates node 3. And now you can see what can happen is that the token will go around the ring and will arrive at the master node while there's still activity on the ring. So here node 3 is still active. So this breaks our simple algorithm. And so we need a bit more intelligence for our algorithm. And that's the algorithm that we are going to model, which is due to Dijkstra. It's a very classical algorithm from the 80s. And it was published in this EWD 840. But the basic idea is the same as I just told you, except that nodes and tokens and the token can be colored. And so we'll use 2 colors, orange and white. And think of white as being clean and orange as being dirty. So the algorithm starts as before. So the master node sends around the token, and it sends a clean token, so a white token. And then, I mean, let us continue the algorithm for a while. So for example, until we reach the situation here in the right-hand picture. So where node 2 is still active and sends a message to node 3, right? And that was the thing that the action that broke our previous algorithm. Excuse me. And what you can observe now is that node 2 sent the message against the direction of the token. So it sent a message to a higher numbered node. And now it will say, well, that was dangerous. That may break my algorithm. So now I'm dirty. So it paints itself orange now. And when the token passes, like here, the token is already there, but it could only arrive later on, then actually the token will take this stain, this orange color, and when it comes back to the master node, when the master node sees an orange token, and it says, well, okay, I cannot conclude this round, something strange happened during this round, I cannot conclude, so I have to send the token around again for another node. Okay, and so the master node will declare that all nodes have terminated when, okay, itself is inactive, it is white, so it is clean, and it also holds a white token. Okay, and so Dijkstra claims in his note that this is a sound algorithm for detecting termination. And more precisely, there are two properties that we are interested in. The first property is a safety property that says, okay, the master claims that it has detected termination only if indeed all of the nodes are inactive. And the second property is a liveness property that says, well, assuming that the nodes become inactive at some point, which is not required, right, but which may happen, then eventually the master will detect termination. Of course, the master will be unable to detect that immediately, right? But after a while, after letting this algorithm run for a while, the master node should be able to declare termination. Okay, so this is the algorithm and the properties that we are interested in. Now let's see how we can model this algorithm in TLA+. So there are two aspects to modeling a system or an algorithm. We have to describe the state of the algorithm, so the system configurations, and we have to describe the dynamics of the system. And so for describing the system configurations, TLA+ uses state variables, much as you would do in a programming language. However, because this is a modeling language, we are not bound to the data types and so on that we get in a programming language. We can use higher level abstractions. And in fact, so TLA+ is based on set theory. So it encourages you to use sets, functions, etc. And so in fact, this is what I said before. This is the set theoretical foundations of TLA+. And for the second aspect, for the dynamics of the system, we describe the system, the algorithm as a state machine. And that means we describe it as the conjunction of an initial condition, usually called init, that describes the possible initial states of the system. So there can be a single initial state or several initial states. So for example, if you have an algorithm that uses two state variables, x and y, you could have something like an initial condition that says x must equal 0 and y is an arbitrary natural number. So as you can see, there's some non-determinism, right? It's just a logical predicate that has to be true in your initial states. And then you describe the possible transitions of the algorithm as actions. Well, that's the name temporal logic of actions that TLA stands for. And so in order to describe actions, you again describe them as logical formulas, but here you use primed and unprimed state variables with the convention that the primed variables refer to the value of the variable in the state after the transition, and the unprimed copy of the variable refers to the value of the variable before the transition. So we could have something like this conjunction here that says, well, the new value of x will be the sum of the old values of x and y stays unchanged. And so you have to write these unchanged predicates, y prime equal y, because otherwise the value of y prime would be completely unrestricted, and that's certainly not what you want. So it's not an assignment, it's really just a logical predicate. Okay, and so you describe the set of all possible transitions of your algorithm in the form of individual actions. And then you just take the disjunction of all these actions to get your next state relation. And the overall specification of the system is then written as a formula of temporal logic. So in the simplest form, it's just initial condition and always next state relation, meaning you start, so this formula describes behaviors that correspond to the executions of your algorithm. And these behaviors must start in a state that satisfies the initial condition, and at every transition that they must respect the next state relation. For the moment, ignore the square brackets, we'll come back to them in a moment. And so as you can see, a specification in TLA+, just as a property in TLA+, is expressed as a formula in mathematical logic. And so we are going to use logical means to reason about these specifications. Okay, so that's the basic idea. Now let's see how that works for our example algorithm. So as I told you, we have to do the static model. So how do we represent the state? And of course, there are many different ways you can represent this. This is the way I chose to represent it here. So a TLA specification appears in a module. So I called this module EWD840, and it has this top bar that just indicates the start of the module. There will be a bottom bar at the end, and there may be any number of these horizontal decoration bars that basically just serve to separate parts of your specifications. Okay, and so the module that I'm writing here imports some modules from the standard library. So here I'm just importing the naturals module that contains basic notions about natural numbers. It declares a constant n that will correspond to the number of nodes on the circle. And as you can see, n is just introduced as a name. It's not given a type, unlike a standard programming language where identifiers would be typed. However, we can introduce an assumption, and that's what I'm doing here. And I'm saying, well, n should be a natural number. And well, a ring with 0 nodes doesn't make much sense, so I'm excluding that case. And then most of the module consists of definitions of operators. So here I'm defining the set of all nodes to be the interval from 0 to n-1. So this dot dot and the minus come from this natural numbers module, and they mean what you expect that they mean. The set of colors, well, that's just 2 elements set white and orange. So I'm just representing colors as strings here. So this is just the constants, right, that I'm using to describe the state of the system. And now the actual state is described by 4 variables here. So I'm using the variables active and color to represent the activation status and the color of the different nodes, and the variables tPos and tColor to represent the current position and the current color of the token. And again, these variables are just introduced without any type declaration. So again, this is all untyped. However, I usually immediately define a type correctness predicate that I call type OK here, so that I remember the values that I expect these variables to hold, right? So active is an array, so it's a function from nodes to their activation status. So just a Boolean, true or false, is the node active or not. Color similarly is a function from nodes to their color. Well, tPos is just a node, that's the node that the token is currently at, and tColor is a color, the current color of the token. Okay, so that was the static part, and now we have to define the dynamic part of the specification. And so I'm defining the initial condition. Now I'm going to relax a little bit with respect to what I said before. It turns out that this algorithm is almost self-stabilizing. So I'm just taking any type correct values of the variables, except that I want to make sure that the token will make at least one round before the master declares termination. And one way to do that is to fix the initial color of the token to be orange. So it doesn't have to sit at the master node initially, for example. And then we'll describe our transitions. And now for this algorithm, I'm going to split the transitions in two classes. The transitions that are actually controlled by the termination detection algorithm and abstractions of the underlying transitions of the system, of the node. So here are the token passing transitions. So the first one, I call it initiate probe. So that's basically the master sending out the token for a new round. And that may happen when the token is at the master node, so the current position is 0. And either the color of the token is orange or the master node is orange. because if both the token and the master node are white, there's no node to send a new probe. We'll just wait for the master to terminate and declare termination. By the way, you may wonder about this funny notation with the conjuncts here in front of this of every line. So this is a convention that we like to use in TLA+ when we have longer formulas, in particular longer conjunctions or disjunctions. We basically write them as bulleted lists where the bullets are either the conjunct or a disjunction symbol. And that allows us to nest these operators and indicate precedence by indentation, like you would have a list and then sublists and so on. And that saves some parentheses. So at first it looks funny, but then you get used to it and you like to do that. Okay, anyway. So when the master sends out a new probe, then the token moves to its neighbor, which remember is node n-1, so it was node 3 in our example. And at the beginning, the token is white, so the new color of the token will be white. And also, we said whenever the token passes a node, then that node becomes white. So we repaint node 0 white. So color is an array, and we update that array in position 0. And in TLA, we use this except notation, which also takes a while to get used to. It's basically a function update. But the activation status doesn't change. And the pass token transition is similar. It just describes the move of the token from a non-zero node I to its neighbor I-1. Okay, and these two types of transitions I call the system transitions. So I introduced the system predicate, and it just says, well, this is either initiate probe, so the master sending out a new probe, or it's some non-zero node passing the token to its neighbor. But this is just a name, so system is just a name like any other name. And then we have two more transitions that model the effect of the underlying algorithm on the variables that we observe, in particular the activation status. And so there's termination of a node, so local termination of node I. So that can happen when node I is active. And then it becomes inactive. So again, we have this except notation to say we change the array active at position I to become false. And the rest doesn't change. And then we have the send message transition. So node I sending a message to some other node. So that can happen only if node I is active. And we pick some node J that's say different from I. And so here communication is synchronous, and this is very central. So that's something that Dijkstra very clearly describes in his node. So node J is immediately activated in the same transition. Okay, and then we have that color. So we saw that on the picture. So if J is greater I, so if the communication goes against the sense of the token direction of the token movement, then node I becomes orange, right? And otherwise it keeps its color. So this funny @ symbol here, that's just a macro to represent color of I. So the old value that we are overwriting. And the token doesn't move, so these two variables are unchanged. And I call these two transitions, or the disjunction of these transitions, the environment transitions. And then we tie everything together as we saw before. So the next state relation is just the disjunction of system transitions or environment transitions. And then we get the overall specification as init and always next. Okay, so far so good, I hope. So I don't see any questions, so please ask if you have any questions. So that was modeling. Now let's do some verification, because after all, that's what TLA is about. And we'll do some standard model checking. So a first property that we can verify is type correctness. Remember, the TLA is on type, so there are no type declarations. The type OK predicate that I defined is just a predicate like any other one. And so we want to check this theorem that the specification that we just defined respects this type correctness, and therefore it implies that the type OK predicate must be always true. So this box means always. Okay, so this is just an invariant that we want to check. And then we have a second property, a second safety property, that was the property that when the master declares termination, we actually have termination. Right, so here I'm declaring a few auxiliary predicates just to make the notation a bit more readable. So the predicate terminated represents the fact that all of the nodes are inactive. And the predicate termination detected is, okay, that's a condition for the master to announce termination. So it holds the token, so the token position is 0. The token is white, the master node is white, and it is inactive. So all of these are conditions that it can check locally, assuming it can look at the token that is currently at the node. And this is the predicate that the master node uses for declaring termination. And the property that we are interested in is that whenever this property holds, so whenever termination is detected, then indeed all of the nodes are have terminated, right, or have become inactive. And notice that termination detected only talks about node 0, whereas terminated talks about all the nodes, right? And again, we express this as an invariant, just as the type correctness above, and we say, well, spec should imply box termination detection. And now we'll use the model checker to verify these properties. Okay, let me just switch to the tool at this point. So here you see the TLA toolbox, and you have exactly the specification that I showed you before. So this is just the ASCII version of the specification. So you see all the different definitions that I had on the slide before. In particular, here we have the overall specification, right? And here we have our termination detection property. And so this is what we now want to verify. And so in TLA jargon, what we have written so far is a specification. And now for model checking, we need to create a model. So a model is an instance of the specification in which we fix the parameters to concrete values. So I will create a new model and give it an arbitrary name. And then you can see here, well, if you can see that, the toolbox asks me for an instance, for a value for this parameter n. So I will give it a value, let's say 5 for 5 nodes. And then what you can see in the rest of this window is, so there's a question, what is the behavior spec? You see in our TLA specification, in our TLA module, we just had a long list of operator definitions. And so we have to tell the model checker, well, which of these operators actually corresponds to the system that you want to model, to your actual specification. So if there's a formula called spec in the module, it will guess that this will be the specification. It will suggest that, but you can change that. And then it asks you, well, what do you want to verify? What are the properties that you want to check? And so by default, it will check for deadlock, and then you can add invariants. So let's just add our 2 invariants. So we had the type OK predicate. So you may wonder, on the slides, I had written theorem, spec implies type OK, and so on. So TLC actually ignores these. These are basically just comments to the users. So here you have to specify the invariants that you want to check. So we had type OK, and we had termination detection. Right? And now let's run TLC. So you click on this green triangle here, and that starts a run of the model checker. And so here it just fires up, and it comes on. And this is the window that you get if the model checker found an error. So up here, maybe that's too small for you to read, but up here it says deadlock reached. And down here, you get the execution that led to the deadlock. So we can look at the last state of the execution. And so we see that here, all the nodes have become inactive. They are all white. The token is white, and it is at the master node. So in fact, this is a situation where the master simply declares termination, and then indeed no action of our algorithm applies anymore. And so that's why TLC tells us, well, there's a deadlock. Okay, this is fine. We are happy with such a state. So this is basically just termination. So let's ignore deadlock checking for the moment. Let's just deactivate it and rerun TLC to see if there are any other problems with the specification. And now it says, no, I haven't found any problem. So that's the image, the window that you get if verification succeeds. And basically you get some statistics on the number of states it has generated, on the number of times it has activated the different actions that you have in your specification, and so on. Okay, so what that means now is that TLC tells us these two invariants are true, at least for this particular instance with 5 nodes. Now you should always be suspicious of success. And since running the model checker is very easy, you can also check non-properties, so things that you expect to be wrong. So for example, you see the token starts out orange, so we could ask, well, is there ever a chance that the token becomes white, or does it for any reason always stay orange? Because if that's the case, then termination detection is trivial, right? Termination will simply never be detected. And so the whole implication is completely trivial. So let's see if we can get the token to become different from orange. So I just go back to my model and add this predicate as a new, okay, that's good. Well, it doesn't matter. As a new invariant to check. And then let's run the model checker again. And it says, no, there's a way to paint your token white. And here is a simple execution, just a one-step execution in which the token actually becomes white, and so on. I mean, you can now check a lot of properties and non-properties just to get confidence in your model, because writing a model is a bit like writing a program. You can easily introduce bugs, except that you cannot run a specification, really. I mean, the way of running a specification here is calling TLC, invoking TLC on it. Okay, let me just go back to my slides. I think I said all of this, right? We said that, we saw that, we verified our 2 invariants. And yeah, this is what I just said. It's a good idea to check properties that you believe to be true, but also properties you believe to be false, and then look at the counterexample that you get to see if that counterexample corresponds to an actual run of your algorithm as you intended it. And in this way, you'll remove modeling errors as you go along. Okay, so that was one part, right? So now we looked at the safety of the algorithm, but we also wanted to have liveness of the algorithm, in the sense that if we get termination, if all the nodes are inactive, then eventually termination will be detected. So we can write this as now a temporal logic formula. So we reuse our predicates that we defined before, right? Terminated was the predicate that says all the nodes are inactive. termination detection is the condition for the master to declare termination. And now we have this squiggly arrow in between, and this is read as a leads to. And so this temporal formula means that whenever the predicate terminated becomes true, then eventually the predicate termination detected will also become true. And again, we will want to check that this is a property of our specification. So any execution, any legal behavior of the specification satisfies this property. And let's go back to our model checker. So I have that definition here, right? This is exactly the formula that you saw. And so let's check it. So I go back to my model. Okay, let's get rid of this spurious, of this non-invariant, right? We know this is false. And now this is not an invariant, so this goes into this other field here called properties. And so I'm adding this down here because this is a temporal formula. And then I rerun the model checker. And now again, I get an error, and up here it says temporal properties were violated. Okay, so now the only temporal property that we were checking was this lightness property. And so again, we get a counterexample. And so you can inspect the counterexample to understand what happened here. And the important thing is down here, it ends in stuttering. So that means it went up to a certain point. Let's see what it got. So in fact, all of the nodes are inactive. And they are all white, and the token is white, and the token is with node 1. Okay, and now what could happen now is that the token simply moves on to node 0, and then the master could declare termination, could declare that it detected termination. But that transition simply doesn't happen. TLC tells us, well, I just continue with stuttering, I do nothing. So this looks a little strange. And in fact, this is built into TLA+. So all TLA+ specifications allow for stuttering steps. So what we got here as a counterexample is a behavior that ends in infinite stuttering. And this is related to this next state relation. So I told you before, okay, the specification says initial condition and always next state relation. But in fact, there are these square brackets and this subscript and so on. And the fine print of this is, well, the next state relation is actually at every step, either we respect the next state relation or we do not change the expression in the subscript. So here we do not change any of the variables. And so we just stutter. So all of the variables remain unchanged. And that looks a bit strange when you look just at a specification of a single algorithm. We'll soon understand why this is useful. So the TLA+ has a good reason for adopting this insensitivity to stuttering. But we need to look a bit ahead to really understand that. Anyway, so finite stuttering is fine, right? I mean, if you buy the idea that stuttering makes sense, that stuttering transitions make sense, then okay, we will allow our system to do nothing for a few steps. But infinite stuttering, so it just stops doing anything. This is a counterexample that we are not interested in. So we want to rule out this counterexample. And the way to rule out such counterexamples is to impose fairness condition. And so a fairness condition is a hypothesis that you add to your specification, asserting that some action will be taken provided it is sufficiently often enabled. And so you can think about that as an abstract representation about the speed of your system components. But getting the fairness condition right can be tricky. And again, the model checker can help you here. So let's look at these fairness conditions. So there are two standard concepts of fairness called weak fairness and strong fairness. And you should really think about these concepts as ruling out behaviors. So weak fairness rules out the behavior. So you want to ignore that behavior. You want to disallow that behavior. If the action that you are asserting fairness for is persistently enabled, so it's always enabled from some point onwards, but it is never taken. And strong fairness is similar, but it has a weaker condition. So the overall hypothesis becomes stronger. So you disallow behaviors where the action is repeatedly, so infinitely often enabled, but never taken, right? So infinitely often enabled means, well, it is from time to time enabled, right? It doesn't have to be always enabled. There may be intermediate states where that action is disabled. So strong fairness is of interest if you have actions that compete, where one action may disable the other one. Here, in our case, we'll see that weak fairness is enough. And so, well, this is where temporal logic shines. You can represent these fairness conditions as temporal logic formulas. So you could write something like this, saying, well, weak fairness for action A means, well, if the action, whenever this action A is persistently enabled, so it's always enabled from some point onwards, then eventually that action A has to occur. And similarly for strong fairness, the formula is very similar, just if you replace this box here, this always enabled, by a box diamond, which means infinitely often enabled. So this would be your standard definition in temporal logic. Unfortunately, this definition is not syntactically valid in TLA+, again, because of these stuttering considerations. So just as in the next state relation, we had to write box square brackets next subvars. So here with the diamond, we have to write diamond angle brackets subvars. So what the real definition in TLA is like this. So I replace the A by a angle bracket A sub V. And this means, well, action A occurs and also V changes. So in our case, the subscript will be the tuple of all variables. So that is saying, well, A occurs and at least one variable must change. So it cannot be a stuttering transition. So in TLA+, you can assert fairness only for non-stuttering actions because stuttering actions are unobservable. Okay, and so what I claim is a reasonable fairness hypothesis for our algorithm is to require fairness for the token passing actions. Right, so that was in our counter example, the token was sitting at some node and that node simply didn't pass on the token. And so we want to rule that out. It could have passed on the token all the time. That was always enabled, but it just never did it. And so we use weak fairness for these token passing actions to rule out such a counterexample. And so let me go back to the model checker. Oops. Let's go here to our specification and let's add the fairness condition up here. Right, that's what we wanted. And then rerun our verification with the same property. And now it tells us it is happy and the liveness property in particular is satisfied and the safety property as well, as we saw before. Okay. Now, in many cases, you would write a specification like this specification here, where you say, okay, I have my initial predicate, my next state relation, and then I assert weak fairness for the next state relation. This is usually kind of the weakest fairness property that you want to assert. And this is just saying, well, as long as something is possible, do something. I don't really care what action you take. And what I'm claiming here is that for this specification, that assumption would be too strong because it would apply not just to the system actions, but also to the environment actions in case no system action is enabled. And so, for example, you could have a node that just never terminates. That is perfectly possible, right? But that node might just be doing just local computations. So never send messages, just work on its own, but never terminate. And that would be a behavior that you want to have. And so here I have a property that I can verify with the model checker that says, well, assume that from some time onward, there are no messages sent in your algorithm, right? And then I claim that eventually all the nodes must terminate, right? So let's check this property with this alternative fairness condition on the next state relation, right? Let's go back to our model. So, okay, let's forget about liveness property. Let's check the other one. And I do that for this other specification that was called spec WF next, I believe. And you see the model checker tells us, yeah, this property holds. So with that fairness property, we enforce termination of the nodes, which we do not want to do. Okay, so this is a too strong fairness condition. Indeed, if you go back to our original specification with just fairness for the system action, we can rerun the model checker. And we get a counterexample that ends in stuttering. And what happens here is that, okay, there's one node that is still active. This node 4 is still active, and the token is just quietly sitting there and waiting for the node to terminate, but that never happens. And that's a fine execution. So here the stuttering simply represents local computation of node 4 that is continuing, right? And this is a valid counterexample. So basically what I wanted to show you here is that you can use your model checker as a tool to validate your specification, just as we did before for safety properties. You can do the similar thing for liveness properties, but you need probably a bit more experience. This is probably much less obvious to understand than what we did before for the safety properties. And that's what I meant when I wrote on my slides that getting the fairness condition right can be tricky for a specification. Okay, we still have a little time left, so I can tell you about an alternative approach, assuming that there are no questions, but for the moment I don't see any questions. So what we've done so far is we have modeled our algorithm and we have verified safety and liveness properties of it. But in a certain way, we could say, well, we haven't really described the problem that the algorithm solves. And we can say, okay, the conjunction of the safety and liveness properties that we check, that's exactly the description of our problem. But maybe we would want to have a kind of different description. And the question is, can we write an abstract specification of termination detection that just specifies the problem without describing the solution, for example, of Dijkstra's algorithm, and then show that Dijkstra's algorithm, so EWD 840, is actually an implementation of the specification of our problem. And we can do that in TLA+, and that's why I want to show this to you, because that's something that you cannot do in other languages. Essentially because TLA+ doesn't distinguish conceptually between specifications and properties. Everything is a temporal logic formula. And so we can check implementation or refinement just in the same way as we check a property. So we'll write a specification TD of termination detection, of the termination detection problem. And so it will have a specification called TD bang spec here. And then we'll show that our Dijkstra specification actually implies this abstract specification. And the key to being able to do that is exactly this insensitivity to stuttering that was a bit strange before. And why is that? Well, our abstract specification will not have the same variables as the specification of the EWD algorithm. In particular, it will not have a token, because a token is a means of implementation. It's not a part of the problem. And so there will be transitions in EWD 840 in our specification that act on variables that do not appear, that play no role in the termination detection specification. And so these steps will just map to stuttering steps for the termination detection problem. Okay, let's make that a bit more concrete. I guess this is pretty mysterious at this point. So let's write the specification of termination detection. And well, I omitted the header with the constants. It's exactly the same as before. And here we just have two variables active as before. That's the activation status of the node. And then we have a Boolean flag termination detected that just tells us, well, now termination has been detected by the master node. And so we again have our terminated predicate saying that all of the nodes are inactive. Now the initial condition is, well, you can have an arbitrary activation status as before. And termination detected, well, it will probably be false, because even if all nodes are inactive, probably you will not know it yet. But who knows, maybe you have a very clever way of knowing that. So if all nodes have terminated, then actually termination detected could be true immediately, right? So this is an abstract way of saying that the initial value of termination of this variable termination detected is either false, so it has not been detected yet, but it can be true provided that indeed all the nodes have terminated. And then we have our transitions. So the transitions that we have here is, well, a node I may terminate. So it has to be active before it becomes inactive. And then again, usually our termination detected flag will not change during that transition, but who knows, maybe we have a clever way and we can detect it immediately if the terminated condition is again true in the post state. Right, so if this was the last node to terminate, then termination might be immediately detected. Why not? And then we have these communication actions. So I call it wake up here. So node I wakes up node J. So here I has to be active, node J becomes true. And here certainly termination detected doesn't change, because obviously they do not terminate. And then we have an additional termination detection transition. So when your nodes have all terminated, then magically you may detect that and set your termination detected variable to true. And this is your abstract way of representing the termination detection problem. Right, so it looks very, very similar to our specification of the algorithm, but now we haven't described the mechanism. Right, here termination detection is magical. Right, the precondition is all nodes are inactive. However, we can detect that, and then okay, we signal we have detected termination, but we don't know how. And because this is a transition system specification, just as the previous one, you can verify similar properties using the model checker. So you could prove that, well, if termination detection if this variable termination detected is actually true, then indeed all nodes are and will always be terminated. And you have corresponding liveness property. If terminated predicate holds, then eventually that will be detected. But what we are now interested in is not so much checking this, that we've seen before how to do that. Now we want to check that our EWD specification, our EWD algorithm, is actually a refinement of this problem specification. So let me go back to the model checker here. So this is the final lines here down below. So I have my sync termination detection module. That's somewhere here, right? This is exactly as you saw before, as you saw on the slides. And then I create an instance of that specification, and I check. I call it TD, and I check that the spec. So this is the specification of the Dijkstra algorithm implies the spec of this TD instance. And so again, I can check that using my model checker. I go back here. Okay, we get rid of those, and I just add TD bank spec as a property, just as I had the other properties before, and run the model checker. It tells me yes, that's fine. So apparently EWD 840 implements this termination detection specification. And now again, you could check to get a better understanding of why this is true. You could, for example, vary a little bit the specification of termination detection and see how that fails, right? But we are running out of time, so I won't do that. The thing that I wanted to remember is that in TLA, you can check both basic properties like safety and liveness properties, but you can also check refinement. So you can compare two system specifications, and you can check that the runs of one specification are included in the runs of the other one modulo stuttering. Yeah, and then there's a variant of that algorithm for asynchronous communication, but I don't have time to say anything about it. So there is an extension of this original algorithm that was suggested a few years later, and that has been published as EWD 998. And actually, if you go, so there's a repository of TLA specifications on GitHub. If you go to that repository, then you can find a TLA specification of that algorithm together with the properties. And so you can verify it in more or less the same way. The main difference being that this adaptation introduces counters, and these counters are unbounded. And so even for a finite number of nodes, you get an unbounded state space. And so TLC will not be able to check that completely. So you will have to introduce some bounds and say, well, assume that the counters never exceed some threshold. Can you then verify the algorithm? Okay, I think we'll break here. So I'll take any questions if you have some questions. And otherwise, we just have a 15-minute break and we reconvene at 45. So 3:45 in Freiburg, whatever that means for you. No questions? Okay, thanks. So see you in 15 minutes. Bye-bye.
Okay, shall we start? It looks like 3:45. 45 minutes. So welcome to the second part of the TLA tutorial. And in this part, I'm going to talk about Apalache symbolic model checker for TLA+. My name is Igor Konnov, and I'm working at Informal Systems now. So let me just find the right buttons. So here's a URL that collects onto the website that collects all the material for this talk. You don't have to download all these things, but if you want to follow and check the specifications later, you can visit this URL, this website. You can find the specs there, the detailed commands to execute the tool, and also a longer version of this talk. So if you want to see the version where I'm talking slower, then you can go on that website and check that version. Perhaps I will not go through all of these slides that I have here, and if I omit something, you can again look at the longer version. So let's talk about Apalache. You can go to this website, apalache.informal.systems, download the tool. We have the manual that explains how Apalache is working. Here you see what kind of basic commands you have to execute in your terminal if you're using Linux or MacOS in order to get started. So it looks like quite a bit to type, but once you have done that, you can run the model checker in Docker, right? So it's all explained in the manual. I'm not going to go in details here. You can go on the website and read about it. What I want to explain you in this short tutorial, I want to give an idea about when Apalache is fast, when it's effective, and when it's not effective. If you have questions when I'm talking, you can feel free to ask them. I can just omit some parts of this talk. I would rather answer your questions than going through the whole talk. So let's talk about clock synchronization. That's a classical algorithm from, that's a classical problem from distributed computing. What kind of problem is that? In clock synchronization, we have several computers or several processors who are equipped with hardware clocks. And the problem is that these clocks are actually, they can be different from each other because the computers can be not synchronized. The clocks may be not synchronized. And these clocks, they can show some values that are close to the global time or maybe not close to the global time. The only thing that we know is that the clock rate of these clocks is the same. So the clocks are advancing uniformly. So the problem of clock synchronization is to somehow let these processors exchange with messages and compute the adjusted clock values. So that these adjusted clock values are probably not equal to each other, but they're in a very close vicinity of each other. What you want to actually make sure is that this property holds true. That when the processes have adjusted, or processors, I will use these things interchangeably. When the processors have adjusted their clock values, for each pair of processes, this difference is less than or equal than epsilon. This epsilon is a bound that actually depends on the number of processes and other parameters. The main point here is that it's pre-computable. You can compute this bound and guarantee that clock synchronization allows you to compute adjusted clocks within this bound. So that's the problem of clock synchronization. Of course, this problem has been explored in the past. If we open the textbook by Hagita T. and Jennifer Welch, we can find this algorithm 20 that solves this problem for the case when processes are not crashing and for the case when the clocks are advancing uniformly. As you can see here, the algorithm looks extremely simple. It just has 6 lines of pseudocode. What happens here is that every processor or process is keeping this difference, an array of differences it has computed. Initially, it sends its own hardware clock value to all other processors. And whenever it receives a message from another process or processor, it computes this delta between the message it has seen, the timestamp in the message it has seen, minus its own clock value, and it also takes the message delays into account. Once it has received messages from all other processors, it can compute the adjusted clock value. So this algorithm, you don't have to understand all of it, but basically there are message exchanges, there is a computation of adjusted clock value, and then the claim that this algorithm actually solves the clock synchronization problem that you have seen above, right? There is a proof in the book, so it does solve this problem. However, if you see this algorithm for the first time, you might ask yourself a question, does it really solve this problem if I don't want to read the proof? And here's one way how you can convince yourself that it works. You can write a TLA specification of this algorithm. And basically in the rest of this talk, I'm going to show you how you turn 6 lines of pseudocode in about 170 lines of TLA+. And of course, if you are coming from the distributed computing community, you will say, wow, why do I need to write 170 lines of TLA+? So the thing here is that actually these 6 lines of pseudocode, they do not capture all the assumptions that you have about this algorithm. In order to understand this algorithm, you actually have to read 9 pages of mathematical text in that book, and then you have a complete picture. So the TLA+ specification captures all of it in one concise piece of mathematical text. So that's why this specification will be longer than 6 lines of pseudocode. So another thing that I want to show you with this talk is that you shouldn't write your specifications just in one big step. Usually, it makes sense to write your specifications incrementally, and that's what we do now at Informal Systems. Basically, what you want to do actions piece by piece. You would produce one version, add some tests for this version, run these tests, introduce more features into your specification, so on and so forth, until the moment that you have implemented specified the whole algorithm in TLA+. Why does it make sense to do it? We have seen that people actually tend to write specifications, very large specifications, without running the tools. And then they end up with having a specification that is not parsable, it's not type correct, it violates a lot of properties, and it's very hard to manage this large specification. You can get a much faster feedback from the tools when you start small, when you start with small versions of your spec and then add features to it. Also, it's important to write some tests, even though you don't need them to verify your properties, such as the skew invariant. So I'm going to give you an intuition about how we do that. Let's start with version 1. So in version 1, I just want to write a very simple specification where we don't have any clock synchronization, we don't send any messages, we don't receive any messages, we only have clocks. Basically, in this specification, I want to describe my environment, just how the clocks are operating. What's important here is that we introduced several variables that describe the system state, and that's a global state, not the state of each individual process. Basically, we want to have this global picture. What we do here, we introduce the variable time for the global time. We introduce a function from process names to hardware clock values, the integers. And we also introduce this function that keeps the adjustments. Basically, this that's a function from from process names to timestamps, or just integer values. If you have followed the talk by Stephan just half an hour ago, he said that there are no types in TLA, and that's true. However, Apalache actually uses type annotations. You see this interesting strings in the comments that say add type colon int semicolon. So basically, since we have to use a logical solver and SMT solver, we have to introduce type annotations in TLA+. They are not affecting the other tools like TLC or TLAPS, but they're useful for Apalache to understand what kind of variables it's dealing with. So we have these variables. We introduce some auxiliary definitions, for instance, the set of processes. And in this example, I just have two processes. I can extend it, and I will do it later. But for now, let's think about the case of two processes. I also introduce what it means for the clock to be adjusted, introduce this operator AC of I. And this gives me the adjusted value, which is just the sum of the hardware clock of a processor plus the adjustment of its clock, right? How do we initialize the system? This system is not doing much. It just has some clocks. And that's what we say. So in one of the initial states, the global time, we don't know what it is. It's just some natural number. The hardware clocks are, again, some natural numbers. So it's a function from process names to natural numbers. And the adjustments are just zeros. So we have this function from process names to zeros. What's important here is that although we are talking about naturals and integers, what's important here for Apalache is that we are actually talking about bounded data structures. We can have a bounded number of counters, a bounded number of integers, or some constants, but we cannot have infinite sets. So in this sense, these expressions where you talk about infinite sets, they should have some special shape. I will not go into detail about this, but that's important to keep in mind. Apalache cannot handle arbitrary TLA+. It always has to work over bounded data structures. So there is a question actually from Markus, why can time become negative? So here, Markus, are you asking about the type or the initialization here? I'm not sure.
Okay, what I wonder about is, so here the type says string to int, and in it, you define the clock to be from processes to naturals.
Yes. So that's a good question, and I get it every time. So it's a good question. So we do not distinguish at the SMT encoding, we don't distinguish between integers and naturals, because naturals are just a subset of integers, right? So from the point, from the types point of view, they're the same for us. We just want to map them to integers and SMT. And there is no special type in SMT for naturals as well, right? So, however, when we want to initialize a variable, we want to use naturals. And basically, we would declare at the SMT level, we'll declare time as an integer variable that is not negative. So we will add an additional constraint on top of it.
Okay.
Yeah.
Makes sense.
So I mean, types, they don't solve all kinds of problems for you here. They're just they're just here to make sure that we can translate things into SMT. Oh, so we have another question. Why is not bounded? So not is not bounded. That's a good question. What's important here is that our data structure that we construct, right? These variables that we have here, like time, HC, and AZJ, these are bounded data structures. Basically, what this constraint is saying that we construct something that has a bounded number of constants, and these constants can be integers or naturals. That we don't care about because that's what solvers can do for us. But what's important is that the structures themselves have some kind of bounded size, right? That's a good question. So in some sense, we have added support for naturals and integers later, and that was very easy to do. But the data structures themselves, they should have some predefined bound. And that's why I'm talking about a finite set of processes here. And that's why I have functions of finite domains here. However, the range of these functions, it can be infinite because I just have to draw a couple of constants out of this range. Yeah, these are very good questions. So, and then once I have defined, these data structures, the only thing I can do, I can only advance clocks because there is not much I can do with that. I introduce this action that basically says, I pick some delta, and here I even say it's an integer. This delta actually has to be positive. And then I advance clocks uniformly. I advance the global time and I advance the hardware clocks. That's as much as I can do with this version. So we can run Apalache, and actually it makes sense to run Apalache now just to make sure that you don't you haven't introduced something strange here, that it's parsing, it's going through the type checker, and Apalache does something. It doesn't do much, I'll tell you what it does, but it doesn't do much here. We just run it, okay? So why is this version of the specification interesting? Because it allows me to explain you what Apalache is actually doing. Yeah, Markus, I'll talk about it later. Keep this question. So I just want to quickly explain you what it means to have bounded model checking here. And this example is very good because it's super simple. So basically what Apalache does, it constructs symbolic executions. What does it mean to have symbolic executions? If you look at that spec that we had, actually all executions like you see here, all executions of length 10 look like this. You initialize time at time point 0 v0, you initialize hardware clocks with two constants C1 and C2, and you initialize adjusted clocks with zeros. Then at the next step, you pick some delta 1, and you increment clocks with this value delta 1. And at the next step, you increment clocks with delta 2, and so on and so forth. So that's actually a symbolic computation. Why is it symbolic? Because we don't know C1, C2, delta 1, delta 2, and so on, right? They're symbolic values. Why is it cool? Because we actually can describe all executions of length 10 just by having this set of constraints. And that's basically what Apalache does under the hood. Of course, constraints are much more complicated because we have sets, functions, and so on. But intuitively, that's what is happening here. You just have a set of equations or inequalities, you throw them at the SMT solver, and you try to solve, and the solver has to solve them. So that's a symbolic execution. How do we concretely encode these symbolic executions? That's what bounded model checking is doing. So for instance, if you look at an execution of 0 steps, basically just initializing our states, we take this frame 0 and write it down as a set of logical constraints. We say that time 0 equals to 0, HC of 1 equals to C1, and so on and so forth, right? Of course, you need some encoding. I'm not going to tell you how we do that, but in case of integers, it's almost like this, like written here. And then what Apalache does, it writes down this logical formula and asks the SMT solver, in this case, it's Microsoft Z3, it asks Z3, is it satisfiable? And Z3 says, yeah, this formula is satisfiable. Here's an example, here's a model. And Apalache says, great, I know there is at least one initial state. So I add one more step. Then it adds the constraints for one more step for the transition that we have seen before, advanced clocks, and asks Z3, is it satisfiable together with the constraints that we had for the initial states? And Z3 says, yes, here's a model. And Apalache says, great, I can continue my execution. It adds one more constraint for 2 steps, right? And then it asks Z3, is it satisfiable? Z3 says, yes, and Apalache is happy. It can extend the execution by one more step. So in a nutshell, that's exactly what's going on in Apalache. So by default, what Apalache is doing, that's what I have explained to you. Basically, at each step, it finds enabled actions, for instance, advanced clocks. It adds a non-deterministic choice of one enabled action among those that are enabled. And then it extends the symbolic execution by one step. So then it's the job of the SMT solver to figure out whether this execution, symbolic execution, makes sense, whether there is a satisfiable, whether this formula is satisfiable, which means there is an example. And then it keeps extending the things until it reaches a bound, for instance, of 10 steps. So if you have one action, it's pretty much like that. You have a set of states, this kind of ball or whatever you call it. Then you have a symbolic transition, which is shown here as a cylinder. It converts this ball into another ball, and so on and so forth. If you have several actions, you again starting with this ball, and you go via one cylinder, the red cylinder or the blue cylinder, and again you obtain some kind of ball. And each of these balls is just a set of states that you can reach within this number of steps, right? So that's like the picture that shows you what symbolic execution is about, and that shows you what actually Apalache is doing. That's intuitively, that's what it does, right? So yeah, what's important here that you have seen, we have these simple constraints, but even in this example, we have infinitely many solutions to these constraints, which means we have infinitely many states and executions. And that makes Apalache different, for instance, from TLC, because Apalache doesn't try to enumerate things one by one. It's just a different approach, right? So far we haven't done anything useful with Apalache. We haven't found any violations. We haven't checked anything. What we can do here is, just as an example, we can write down some kind of an invariant which we know is violated and check it with Apalache. Basically, what I want to check here is this naive invariant, which says is that for every pair of processes, the adjusted clock values are equal to each other. And we know this is not true, right? Because I even didn't write clock synchronization here. So to do this, we basically get these constraints for the initial states and write down the negation of the invariant candidate. Now we ask Z3, is it possible to find an example of such an execution that violates this invariant? And Z3 says yes. And Apalache says, great, I have found an error. And that's what it's going to do here, right? I run Apalache, say, and I tell Apalache, please check this invariant. Then it runs, and even in the initial state, it finds the violation of this invariant candidate, right? And the violation is very simple. We just have different hardware clock values here, right? So I don't have time to go in details. I have this detailed talk for you. You can watch it later. What I want to stress here is that it's very useful to write tests even for very simple specifications like this one. What I do here, I basically write some kind of test fixture where I tell how to initialize the states, and I tell how to make the next step. What's important is that I want to test this action in isolation. I don't want to test all possible actions I have. Here I just have one, but in principle, I just want to have this one action. And even here, I can write some meaningful invariants. I can say that, for instance, hardware clocks and the global clock are not decreasing. And that I can run, this test I can easily run and test with Apalache. So I don't have a lot of time here. Again, look at the longer talk. Basically, what we're about to do here in this specification, the second step, we want to send messages. To this end, we introduce constants that tell us what kind of delays we have, the minimal delay, the maximal delay, and we introduce a set of messages that will keep track of the messages that have been sent. Plus, we have some kind of control state. That's how we send messages. We just add a new message to the set of all messages that have been sent so far, and nothing interesting has happened here. Just keep sending messages. Again, we can test this thing. Now this fixture becomes a bit more complicated, but the trick here is that, again, you want to keep a bounded number of constants. They can be integers, but the number of them is still bounded. We run the tool, it tells us that this holds true. I'll just skip this one. How do we receive messages? Well, receiving messages is getting interesting. You add again a set. You add this variable that keeps the received messages, and now not only you have to add this message into the set of messages you have received, you also have to add constraints on the stamps and the clocks. You have to add these constraints somewhere. Basically, you say that you don't want to receive a message earlier than tmin, and you don't want to advance clocks beyond the point when some messages haven't been received, although they should have been received. And this is very interesting because you don't see it in the pseudocode, just nowhere in the pseudocode. However, in the TLA spec, you have to be precise about it. You have to write it. So your model, computational model, comes together with your algorithm, basically. So that's how we receive messages. Again, I skip that. How do we adjust clocks? This is like the least interesting thing here, actually. We just take basically what's written in the pseudocode, and we compute this delta, which is talking about the minimal and maximum delay, divided by 2, take the difference. And here we do adjust, I think it's according to the formula. I just write it down for 2 processes because it's easier for this example. I can write it in the general case as well. So we adjust clocks. We specify what it means to have bounded clock skew. And it looks a bit larger than the original property, but that's because I'm dealing with integers here and not real numbers or rational clocks, right? And so I have to play with integer multiplication instead of doing division. So I did that. Again, you can check the longer version. And then Apalache told me there is a bug, which I didn't believe because the algorithm should be correct, right? So it did these computations. I think this is a bit faster than actually the actual clock. So there is a counterexample. And then I looked at the counterexample, it said, look, you're actually adjusting your own clocks. And I was surprised, why should the process adjust its own clocks? And I looked at the pseudocode again and said, aha, so actually I have to receive messages from other processes, not my own messages. So that was my mistake. I went there, fixed the pseudocode, the specification, right? And then it went through. So now I must be happy, right? My invariant is not violated, at least in a short number of steps. Things work. You see, you need like 2-3 minutes to run the tool. And then I'm done, right? The question is whether I'm actually done. Because now recall that we have fixed values for tmin and tmax. What shall I do about them? Maybe things do not work for different values of tmin and tmax. And actually they don't. So now what we can do in Apalache, we can say, instead of checking the specification for fixed values of tmin and tmax, we just check for all values of tmin and tmax. We write this constant predicate, give it to Apalache. Also, we assume that tmin is less than tmax, that's important. And then we find a bug due to integer rounding because we are not using rationals here, right? I have a very simple solution here. I just extend the bound to account for integer rounding. A better solution would be to introduce rationals here and write the specification of rationals, but that's too much work, right? And that's too much for this small example. So basically, we have checked this specification. It's doing something. What can we do next? And here I'm going to finish, so don't worry. So what I did, right? I have extended the specification for arbitrary sets of processes. I cannot check it for arbitrary sets of processes because Apalache needs bounded data structures, but the spec can be written for an arbitrary number of them. Then I checked all the unit tests, and again, it's important. I think it's important to keep track of the things you have been doing, not just forget about them. And I can check the spec for a small number of processes, 2 and 3. I can check it for arbitrary values of delays, tmin and tmax, but then the tool is getting slower, which like any other tool, right? What we can do here, and I'm not going to talk about it, we can check an inductive invariant here, which will give us guarantees for arbitrary long executions, first of all, and second, usually checking inductive invariances faster than checking long executions, long symbolic executions. I think I will stop here. If you want to learn a bit about inductive invariance, you can check the longer talk. I'm not telling you how to check the inductive invariant here, but I think we'll prepare another talk. Just check the Apalache Twitter or the Apalache website from time to time. So that finishes my talk. Thanks a lot, and I'm ready to answer questions if you have any. Oh, actually, I forgot to tell, there is Apalache GitHub. You can post issues there. There are bugs. We expect them. We have the Zulip chat where we have some kind of interactive debugging sessions. Yeah, just join the chat and go on GitHub, ask questions there. So yeah, I guess there are a couple of questions here. Sorry, Stephan, taking away your time. So Markus is asking about reals. I guess I have more or less answered this question, right? I'm just having integers here. I could write rationals. I know how to do it, but it's just too much for this example. Then what are the best practices to determine the bound for Apalache? Well, that's a good question. I mean, in practice, you try to go as long as you can, right? I think it stops working efficiently after 15, 20 steps. That's like a rule of thumb. Sometimes it can go for 1,000 steps, but it's basically for deterministic programs because you do propagation. And then we have non-determinism, it starts getting slower much fast, very fast, right? So I think the real answer to this question is to use modularity. Try to write these tests I was talking about and try to check inductive invariance. That should be the approach to decompose your problem into smaller pieces. And Alexander Niederbull is asking about inductive invariance. Can an inductive invariant replace a formal proof? Kind of yes, but not always. So if you only have, say, a fixed number of processes of bounded sets, then yes, inductive invariants give you complete guarantees because you can talk about infinite executions. But if you want to check things for infinitely many processes or just an unbounded number of processes, then Apalache won't do it for you. It cannot do this kind of parameterized model checking. That's where you have to use a proof system. And this gives us a very good follow-up because I don't think Stephan will talk about this specification, but that's in principle what the TLA proof system is good for. You can check inductive invariance there for all kinds of parameters. So yeah, that finishes my talk. You can ask questions in this fireside chat session that we have at some point later. Thanks a lot. I guess Stephan, I give room for you. Sorry for this 3-minute delay or something like that.
Thanks a lot, Igor. And as you said, that is kind of the perfect transition now to deductive verification. Okay, so I'm back here, and so in this part of the tutorial, I wanted to show you, give you a glimpse of the TLA proof system that we are building for deductive verification of TLA specifications. And so, yeah, we call it TLAPS, TLA plus proof system. So it's a proof assistant, an interactive theorem prover, and it is a different kind of verification game than that you've seen with TLC or Apalache. So the advantages and the disadvantages for using a proof system. I would say the main advantage is that you don't have to care about the size of the model or your state space, right? So in the example that I showed you, the EWD algorithm, we use TLC to model check the properties for rings of size 5. We could have gone a little higher, but eventually the state space becomes too big, and TLC will run out of steam. And Igor basically said similar things, right? You have to have a bounded data structure. You have to ensure that you can encode your state space using a bounded number of variables. So again, the size of the model, the size of the instance that you're looking at is a critical parameter. So this is not at all an issue when you do deductive verification. So that's the good news. The bad news is that, well, it's an interactive tool. So you as the user have to write the proof, and the tool is just there to check that it accepts your proof. So it is more work. It is not just pushing a button essentially. Okay, but let's see how we can do that. So I'm going back to this EWD 840 algorithm, the termination detection algorithm, and I'm basically going to verify the same properties, but now independently of a fixed n. So I'm going to prove these properties for arbitrary n. And so the first property that we were interested in was type correctness. So this is now our theorem. We want to prove spec implies always type okay. And this is the way we can write the proof. So this is a simple invariant proof. So what you do is you show that the predicate holds in the initial state. So the initial condition implies the type correctness. And the second step will show that type correctness is preserved by all possible transitions. So if you start in the state where type okay is true, and you do any next step or stuttering step, then type okay will still be true in the post state. And that should be enough. And so this will be the QED step. And it's just checking that this outline of the proof is correct. So remember, we haven't proved steps 1.1 and 1.2 yet. These are just assertions. But assuming that we will be able to prove them, we can check that this implies our theorem by using these steps 1.1 and 1.2 and a decision procedure for propositional temporal logic that's called PTL here. Oh, and then we also have to unroll the definition of spec, because you see steps 1.1 and 1.2 talk about init and next. The assertion talks about spec. And so we will have to tell the prover, well, unroll the definition of spec, and you'll see it's just init and box next and maybe some fairness condition. That doesn't play a role here. And so this is enough to prove everything. Okay, so let's do that. I'll just go back here to my TLA specification. So here we have our lemma, and so I'm checking this last step, this QED step. So I'm just invoking the prover, and you see that turns green. So the prover has checked this proof step, and it accepts it. Okay, so if I check the entire theorem, so if I invoke the prover from up here, then it is colored yellow because, okay, the last step is fine, but the other steps are yet unproved. Right, so now we have to prove the steps 1.1 and 1.2. So showing that the initial condition implies type correctness, that should be very easy. So if you think that something is obvious, then you can write it like this in TLAPS. Well, let's check it. And it says, no, I cannot prove that. And here it gives you basically what it was trying to prove and what it failed to prove. And we can see it's just the context, right? Our constants and variables. And then we have to prove our implication, but we don't know what init means and what type okay means. So this is just proving P implies Q for arbitrary predicates P and Q. So obviously we have to unroll the definitions of init and of type okay. Okay, it takes a little longer, but it still fails. I'll just kill it. And okay, so you see these are the unrolled definitions of init and type okay. And the two formulas are very similar. However, there's a difference. Here, the last conjunct on the left-hand side is T color equals orange. And on the right hand side we have T color in color. So basically it doesn't know that orange is a color, so we have to use the definition of color as well. And now it's happy. Okay, and now we have to prove the other step. And okay, you can try the same game and just unroll all the definitions and so on. And maybe that will work, or maybe that will not work. Let's assume for the sake of the example that it won't work, because at some point, if your formulas get too large, then the automatic provers will not succeed anymore. And in that case, you have to decompose your proof further. So what you may have observed here is that my 3 steps here, they all have this number 1 here, and this basically means they are steps at depth 1 at the top level of the proof. And so now I'm going to introduce a new level and decompose my proof, and we actually have a small assistant for that, so I can show you how that works. If that comes up here, maybe that's screen sharing, but what's happening here? Why don't I have decomposed proof? Seems to be an interface issue. Okay, let's leave it at that. So if that would have worked, basically it would have inserted it as this skeleton of this proof without the leaf proofs. So we would have gotten a number of labeled 2 steps with the initial proof step and the final Q step, QED step already filled in, and let us then do all the leaf proofs. And so for this proof, I'm just saying, okay, I'm going to use my assumption that n is a natural number all the time. I'm going to use my definitions of type, okay, nodes and color all the time. So just use them globally, so that I don't have to type each time to state explicitly that I want to use to unroll these definitions. And so, for example, I could just go to this case here. So this is my first action. Right. So the idea of the proof is you prove preservation of type correctness, not just for the overall next state relation, but for each of the individual actions of the algorithm. Right. And then I could say by def initiate probe, for example, and see if that works. And again, it will not work. Okay, let's kill it. And so what happened here is, so here on the left-hand side, so among the assumptions, we have our type okay predicate that's assumed for the pre-state, and we have to prove it for the post-state. And it also knows that, okay, there will be a next step, but that doesn't help us very much because we don't know what next is. The thing that to observe here is that the initiate probe action is missing, right? So we said it will use the definition of initiate probe, but actually it doesn't even occur here. And this is a pitfall that each of us falls over all the time. So actually this case here introduces a new assumption. It says, well, assume we have an initiate probe, now prove your current obligation. And so we have to explicitly use this assumption, and we do this by writing 2-1. So that looks a bit strange because it looks like you are using the assertion that you are trying to prove in the proof. Actually, the meaning of this 2-1, if it occurs inside the proof of the step, is we'll use the assumption of that step in the proof. So we discussed for a while, and then we got used to the notation that it just stayed like that. Okay, and now we can try again, and now it works, and it will work in the same way for the other steps. So basically, if you just let the prover work, then it will show you, okay, type correctness is fine. So that was nice. Now let's look at our second safety property, the one that, okay, this is type correctness that we have seen, so I can skip that. We have seen all of this. Okay, this is our main safety property, termination detection, right? Whenever the master claims it has detected termination, then indeed all nodes are inactive. And if we try to do a proof of the same shape as we had up here, just this 3-step proof, then this will not work. So we would prove that the initial condition implies termination detection, that would be fine. And then we would have to prove that termination detection is preserved by any action. The problem with that is that termination detection only talks about the state where the master detects termination, not any other state. So in particular, for example, assume that you are in the step where the master receives the white token, gets the white token back, and will then declare that it concludes termination. Then we don't know anything about the system, because in the previous state it couldn't declare that. So our inductive assumption doesn't help us in any way. All right, and that's where you need inductive invariance. So we need an inductive invariant that gives us enough information about all the reachable states of the system. And the problem is in deductive verification is to come up with inductive invariants. Usually these are difficult to find, but if you have them, they are very valuable because they give you a lot of information about your algorithm. So now, fortunately, for this algorithm, we can look at Dijkstra's paper, and of course, Dijkstra provides a proof. He is very careful, very meticulous, and so he has an inductive invariant in the paper. And so here I just copied Dijkstra's inductive invariant. And so it is written as a disjunction. It says, well, one of 3 cases must always be true. And so we can check, well, why is this invariant interesting for proving the termination detection? So we are assuming the master declares termination. Now, if we go through the disjuncts from bottom to top, the last disjunct says, well, maybe the token is orange. Well, no, if the master declares termination, then it holds a white token, so the token cannot be orange. So this cannot be true. So what about the second disjunct? It says, well, there exists a node between 0 and the current token position that is orange. So when the master declares termination, it holds the token, so token position is 0. So this interval is just a singleton 0, and we would have a color of 0, so the color of the master node equal orange. But no, the master only declares termination when itself is white. So this can also not be true. So the first disjunct must be true. And the first disjunct says, well, for all nodes that are greater than the current token position, which is 0, so for all the non-zero nodes, all the non-zero nodes are active. So that is good, because termination detection tells us, oh, and the master node itself is also inactive, right? And therefore all the nodes are inactive. And so this inductive invariant will, well, this claimed inductive invariant will actually be good enough to prove termination detection. Okay, still, if you have such a predicate that is claimed to be an inductive invariant, well, before starting to do the proof, which may be tedious, it's a good idea to do model checking again. And so we can, let me go back to my model. This is still open here, right? And okay, so how do we check using TLC? I mean, Igor basically hinted at how you do it using Apalache, but how do you check an inductive invariant using TLC? So here's the key. You replace the initial condition of your specification by the invariant that you're interested in. So you say, well, take any state that satisfies the invariant. Okay, here I'm also throwing in type correctness. We already know that type correctness is an invariant, so we can always add that. And so I'm saying take any type correct state that satisfies the invariant, and then do any steps. Right, so I'm replacing the initial condition by the predicate that I'm interested in. So let me just copy that name. So I'm replacing again my specification by this specification here, not by the whole equation, whole definition. Okay, let's forget about the properties, and what we are interested in is our invariant inf. Right, and then again we call TLC. Now TLC will do model checking for our 5-node ring. And it says, yeah, this is true. And the interesting thing here that you see is the diameter is only 1, and that is what we expect, because well, we're starting from a state in which the invariant holds, and basically as soon as we do one step, we hit another state that we had already seen, because it again satisfies the invariant. Okay, so this is a way to validate your inductive invariant. And once that works, then you can prove the theorem. And now the outline is as follows. So because we are proving our inductive invariant, so we show that it is true in the initial state, that it is preserved by the next state relation, again, modulo type correctness, which we already know to be an invariant, and that it implies termination detection. That was the argument that I had above, that this is a useful invariant. And again, then we can use our proof checker to make sure that this all holds. And let me just go back here to the module. Oh, by the way, I forgot to say that the slides as well as the models are available from the tutorial webpage, so you can play with them yourself at home. Right, and here we have the proof. Okay, so again, we used our assumption, and we show that init implies invariant. This is as before, basically. And here we again have a one-step proof. So here, just unrolling all the definitions works for showing that our invariant is preserved. Similarly here for showing that invariant implies termination detection, and that completes the proof. So we can just check it. And yeah, again, no problem for the theorem prover. So as you can see, I mean, as soon as the proof is correct, it is usually checked quite quickly. What may take some time is to actually get it right, of course, and that's the time, that's the effort that you don't see in this presentation. Good. So far, so good. So we proved safety. Okay, so this is just an outline about the tool. I think I'll skip that in the interest of time, and I'll give you just a hint of how you can use TLAPS to prove Leibniz properties. Now, a disclaimer here: if you use TLAPS and the current TLAPS distribution, you will not be able to carry out this proof. This is using a development version of the proof assistant, but I still wanted to give you a glimpse of how you will be able to do that in the upcoming release of TLAPS. Okay, so this is just a reminder. This is the property we're interested in. I want to show that, assuming that all the nodes are inactive, eventually we will detect termination. Okay, so how can we prove that? So how will it actually work in the algorithm? So I'm assuming I'm starting in a state where all the nodes are inactive, right? So we have only single circles, but okay, the token may be somewhere in the ring, and some of the nodes may be orange, or the token may be orange, whatever, right? So this may be a state where where terminated holds, because now the last node actually terminated. And okay, so the first thing that we have to do is to bring the token back to the master, but here the token, well, it sits on an orange node, so it will pick up this orange color. And so it will be orange when it goes back to the master, but at least we have the token up here, and there may still be some orange nodes along the ring. So the master cannot conclude, not termination detected does not yet hold. And so we'll have to repeat. And now the token again moves around the ring, and what will happen now, so it will start out white, but then it will collect the orange color, the dirt from all the nodes that are still dirty, right? So when it comes back to the to the master node, it will again be dirty. It may again be dirty, right? But we have made some progress because now none of the nodes is dirty anymore. They are all clean. And so now we send the token once more, and now there's no more dirt to collect. So it will come back white. And then the master can say, okay, now I detect termination, right? So this will be the idea of the proof. So what this shows is that you may need 3 rounds of the token from the state where all the nodes became inactive until the master can actually declare termination. Okay, now how do you actually set up this proof so that it works in the prover? It is usually the case that for proving liveness, it's a good idea to do a proof by contradiction. So what I will actually show is I will assume that termination is never detected. Okay, as I said, I throw in type correctness. We know this is an invariant, that is fine. I'm assuming that termination is never detected. The rest of the spec is unchanged. And I prove liveness, my liveness property under this contradictory assumption, right? And this will be enough then to conclude that the same property holds for the original specification. And the prover will be able to figure that out. Okay, so this will be the setup of the proof. And now basically the one thing that I want to show you that is new with respect to the distribution is how we handle the fairness. Right before in model checking, we saw that here the fairness condition was essential because otherwise you get stuttering executions and you will never get progress. So we have to exploit the fairness condition that we have in our specification. And remember, fairness was defined in this way, right? If the action is forever enabled, then eventually it must occur. And that means if you want to reason about fairness, we have to reason about this enabled predicate. And the enabled operator, so this is an operator of TLA plus, but it's one of the most complicated operators of TLA plus. It's kind of a modal operator. It is an implicit binder for primed state predicates. And so in order to make the proof manageable, we want to reduce this enabledness condition to a simple state predicate, right? We find the state predicate P, and we show that this enabledness condition is actually equivalent to the state predicate P. Yeah, so how do you do that? Well, there are basically 2 ways of doing that. Either you just use the definition of enabled, which is like this, okay? Enabled of angle A sub B means, well, there exist values for all the primed variables V, such that A holds, and V prime is different from V, so we get a non-stuttering step, excuse me. Right? And so this is basically what you can do. You can expand this this enabled predicate and then reason about this explicit quantifier. The problem with that is that introducing quantifiers is always difficult for the backend provers. It makes their life harder. And the fact that you have this non-stuttering conjunct in there creates extra complications because you have to find the witness not just for your action, but also one that ensures non-stuttering. So usually it's a better idea to use some specific rules for simplifying this enabledness condition. And this is what I'm going to outline. So the first observation is that in our example, and indeed in most reasonable specifications, the steps, the transitions that you specify are actually non-stuttering transition. You rarely specify a stuttering transition. And so here, you know, system transitions are those token passing transitions. So it means the token passes to the neighbor, and so that this rules out stuttering because the token moves, right? And so this is just a regular action level reasoning step. This is the standard way of the standard type of proof obligation that we that we know how to deal with. So we'll assume we can do that. But now the enabledness predicate is actually monotonic. So if you have action A implies action B, or action A is equivalent to action B, then you can conclude that enabled of A implies enabled of B, or is equivalent to enabled of B. And so this is just, we will apply this reasoning step to get rid of this non-stuttering conjunct, right? And say, well, enabled of a non-stuttering system is actually just enabled of the basic system action. And so there's a special proof directive in TLAPS now that enables you to do that. And then we are left with figuring out what enabled of system is. And for that, we'll push the enabled across logical connectives. So we can observe that enabled commutes with disjunctions. Enabled commutes with conjunctions, provided that these conjuncts do not share primed variables. And so this is particularly useful if you have, for example, A equals X prime equals something and B equals Y prime equals something else, right? Then you can separate them. Then again, if you have this form of equalities, enabled X prime equal T, where T doesn't have any prime variables, well, this is just true because this is just saying, well, there exists a post state in which X has the value T, well, just give it that value, that's fine, right? And similarly, if P is a state predicate, so in particular, all the preconditions of an action, then the enabled just disappears. And if you apply that, so there's another proof directive called enabled rewrites that pushes enabled across all these operators. And if we do that, then here we get our proof, right? So here I'm defining the enabled predicate for this system action, and it's just the disjunction of the explicit preconditions that we have in the definitions of these two actions. And then, yeah, then this is a three-step proof. First, we show, okay, stuttering doesn't play a role. Therefore, it doesn't play a role in the enabledness predicate. And then we just apply our rewrite rules and expand the definitions, and it goes away. And now we have an explicit representation of the enabledness condition. And this is the main step. The rest is temporal reasoning. And I won't have time to show that, but that actually works with the current distribution. So basically that we know how to do. It's just a mix of inductive reasoning about the nodes. So to make sure that the token will indeed circulate from one node to the next, mixed with temporal reasoning. And okay, so you have three lemmas that basically correspond to these three rounds that I showed you. And then with these three lemmas and the type correctness that we showed before, we can conclude that we get our liveness property. And notice that our lemmas talk about this B-spec, this specification with the contradictory assumption that we never declare termination, whereas our final theorem talks about spec, but the temporal logic decision procedure is clever enough to figure that out. Okay, so that brings me to the end of this tutorial. So we've shown you the language TLA+, and I think we've insisted a lot on its mathematical nature, which is different from what most computer scientists would probably design as a specification language. So we use the set theoretic language to describe the state, and then we have state machines for representing the behavior. You can use it to verify properties, but also refinement. There's no fundamental distinction between the two in the language, in the formalism. And there are tools that support that. So you have the toolbox, which is your basic editor, your GUI that you're using for interacting with TLA+. And there's the explicit state model checker TLC, there's the symbolic model checker Apalache, and there's the proof tool, the proof checker TLAPS. We haven't talked about Plascal, which is a kind of pseudocode language for generating TLA+. And yeah, here's the link to the TLA website. So there you get a lot of information There's also a Google discussion group that you are very welcome to join if you have questions. We and other users of TLA Plus try to be helpful and answer questions. Okay, so that's the end of the talks. Now I see a question from Markus. How does proving liveness work with refinement? Okay. So do we need this existential quantifier over state variables? Yes, in the end, we need that. So as long as you have only refinement mapping, so as for example with proof that the EWD840 algorithm is an implementation of the termination detection specification, there we only had to substitute variables in the abstract specification by terms of the algorithm. Then you don't need this explicit EE, it just disappears through the instance. If you have refinement proofs that require auxiliary variables like history variables, prophecy variables, and that stuff, then you would need special rules, and we don't have support for that yet. So this is future work in TLAPS. Igor. Is it easier to prove liveness when we know enabled is independent of primed variables? I'm not sure I understand what means independent of primed variables.
Yeah, maybe I can refine it a bit. I mean, it often happens that you only have the essential part of enabled in your precondition, which is talking about unprimed variables, right? And then what concerns primed variables is just x primes equals 1, for instance.
Exactly.
Right. Yeah.
Exactly. So this is this is this rule here, right? Enabled x prime equal t equal true. This just disappears.
Yeah, yeah. And then you take into account the unprimed variables only, right?
Yeah.
In this case. Yeah. Okay, perfect. Yeah. Cool. Thanks a lot.
So is there any reason why PTL is not included with TLAPS by default? Okay, so I mean the tool, so PTL refers to a decision procedure. It is included in the distribution. I guess what you mean is why it is not invoked by default when you write a by proof. Well, that is a good question. So this is partly historical because it came later, and partly, I guess, because it is so temporal logic is used only in very few steps, and so maybe we thought that it was useful to make these steps recognizable. Right, but I mean, in principle, there's no reason why PTL could not be tried by default, just as we try other backends. I didn't talk a lot about that, but TLAPS actually invokes different automatic theorem proving backends for first order reasoning, but not for temporal logic. Yeah. Second question, are there any guidelines to writing TLA plus specifications? Yeah, so this is pointing to a larger problem. So there is currently very, very little documentation for TLAPS. This is on my to-do list to write a real tutorial for TLAPS. And that would include such guidelines, but I mean, this will be a community work. I mean, I cannot do this by decree. I mean, I can only write what I'm aware of, and I'm sure that there are many other things to take into account. Actually, so yeah, even that a similar question could even apply to TLC. So TLC and also Apalache. I mean, TLA plus is such a broad and expressive language that no tool can handle an arbitrary TLA specification. So I guess TLC has been around for so long that users have become used to what TLC can handle and write their specifications in this form. The other tools impose different or additional conditions, whatever. So yeah, that will have to come with time. is the developer version. Yeah, it is available. It is on the website. So if you download and compile yourself, if you're brave enough to do that, then yes, it is in principle publicly available. Ask me if you need help. Okay, I think we almost started fireside chat questions already in this way. I think we should maybe still take a little break if people don't mind. And so, okay, so we're a bit over time, right? We are running like 10 minutes late. Should we say a 10-minute break and then we do this chat session?
Yeah, makes sense.
Okay, so see you in 10 minutes.
So who wants to open?
Maybe we should just start.
Yeah.
So Markus, why don't you take the lead? We've already talked a lot.
I just wanted to follow up on what Igor said about reals and rationals in Apalache. Have you done this in practice, an algorithm that deals with reals and rationals and those effects that appear in this area?
Not really. I mean, for this example, I actually started to write the rational module, right? It's not so hard for this case because you don't need a lot of operation there. It was even shown some examples. Model checker was running, but then I figured out that I could just increase the bound and make the example simpler. That I think for rationals you can implement things. The question is, of course, what kind of operations of rationals you need. The basic arithmetic, I think it's not complicated. For reals, I think SMT supports reals, right? But I haven't seen an example where people would tell us they need reals. And of course, SMT, I don't think it will let reason about pi or e, right? All these transcendental numbers. So yeah, it's kind of a neat feature, but I don't know. Maybe Stephan has more insights about reals. I can see examples.
Well, I mean, depends again. It depends, as you said, on the operations that you need, right? I mean, if you really need reals and not just rationals, then probably you are thinking of, I don't know, trigonometric functions, or I mean, certainly not just polynomials, right?
Yeah, I wonder if better support for reals in TLAPS or the TLAPS tools in general would unlock a different kind of problem set that engineers face and would want to solve with TLAPS. If we are kind of missing a bunch or a group of users because there is no better support or no real support for reals, they would like to, yeah.
Yeah, well, if you think of hybrid systems, I guess they might be interested, right?
Yeah.
And yes, we certainly do not support that.
I think we have the first question. Maybe I just read it out loud. What prerequisite in terms of general reading material would you recommend for a newbie to TLAPS? I have used TLC for checking my specifications, but a transition to TLAPS appears rather involved.
Yeah, I think your impression is correct. I would certainly support that. Okay, so if you go to the TLAPS website, there's a basic tutorial about proving some properties of Euclid's algorithm. And then in the distribution, you have a number of examples, of worked out examples, ranging from Peterson's algorithm for mutual exclusion to Paxos, things like that. But yeah, as I said, basically at the moment, unfortunately, you're pretty much on your own. I mean, you're always free to ask, and feel free to ask. You're welcome to ask, and we'll try to help you out. But clearly, we need better documentation.
So, if people want to help with the documentation, they just join or open an enhancement request at the GitHub repository, or how do you think this would work?
Sure. I guess in order to be able to contribute to such documentation, you have to have some sufficient experience, right? And yeah, you can always ask for help. And I mean, there are a few experienced users, right? I mean, there are people from outside of our group who've written involve proofs for different variants of Paxos, for example. And I was always amazed how they managed to prove that Ur, who's here, wrote proofs, wrote TLAPS proofs. So there are brave people who managed to fight their way through the tool without much help from us. But yeah, I mean, we clearly have work cut out for us. Yeah.
So what I wonder about, perhaps a question for Igor, what's your vision of how the three tools, TLA, TLAPS, TLC, Apalache, work hand in hand together in the future? Or what areas do you see covered by which tool? What do you think is the workflow, the usage pattern for engineers? What's the usage pattern for academics that are more interested in writing proofs? What is the kind of the workflow that you envision?
I mean, that's a good question. I mean, what we have experienced in the last years, I think, with Apalache, that the way you write specifications for TLC and Apalache is a different phase. If you heavily optimize your specification for TLC, there are good chances it will be slower in Apalache. If you look at this specification and optimize it for Apalache, there are good chances TLC will just complain, oh, you have integers, go away, right? So I think it looks like that Apalache is somewhat in the middle between TLC and TLAPS, you know, in terms of what kind of specifications you want to see. Because TLC, to use TLC, you need some kind of small domains, very small domains, actually, right, to make it work. For Apalache, you can have large domains, so integer constants, as you have seen. But again, it hits the limit very quickly, right? So, I mean, I think it very much depends on your problem. And if you're an engineer and you have a good intuition about how you would do a finite state model, you know, there are some examples where you can do finite state abstraction very easily. If you have a good intuition about that, I would tell you to go with TLC. Try TLC first. If you have examples where it's just very hard to tell what kind of finite domains you will use, for instance, something like smart contracts, it's sometimes very hard to say how you do operations over tokens if you have like 5 values. It's just hard to imagine, right? I think there you start with Apalache, and maybe then you find an abstraction that works better for TLC, right? So TLAPS, my impression of TLAPS is the most encompassing one. Of course, you don't want to enumerate cases, a lot of cases in TLAPS. But the transition from Apalache or TLC to TLAPS, I guess, is easier than, you know, the transition between Apalache and TLC somehow. That's my impression now. But there are definitely specs that work well both in TLC and Apalache.
Maybe a follow-up to that. At least what I find kind of overhead right now, maybe that's too strong an notion, but these type annotations in Apalache, I would prefer if I could just throw at least initially my specification, my plain specification at Apalache, and then for at least the simple case that just has type inference, automatic type inference, and only for the hard cases perhaps needs some special assistance. So what's your midterm plan on relaxing the requirement to have type annotations?
Yeah, I mean, it's basically the type checker that we have now. It's the third generation already, right? So I think I just want to stop working the type checker for some time. I don't want to write more code on it. And in the middle, like the second generation of this type inference tool that was fully automatic, it was using SMT. And as you say, sometimes it just infers things and it works. But surprisingly, it actually was hard to, let me just close the door. It was hard to figure out what kind of errors you have. So if you have a specification, this huge specification, the type inference tools tells you there is an error. It's a global specification and you have some kind of global type error. That was very hard to debug even for us knowing how the tool is working. What we like about the current type checker that it uses some form of locality. Basically, it does over operator definitions. And if it doesn't manage to infer types within this operator definition, it complains right away. It says, I cannot infer types, right? And it gives you reasons. Since operator definitions are relatively small, the reasons are understandable. I mean, some messages are still incomprehensible, but it's easier to understand, localize your type error. And what I also like is that you can go and introduce notations to all operators involved, and this will even give you a better sense of where the error is happening. With a global type inference, I think it's the same, for instance, with a camel. If you have a program and you run global type inference, it might show you an error somewhere, although the source of this error is somewhere else. I actually experienced it with a camel as well. So this locality, I like it actually, and people say they like it. Our users say they like it, right? So I kind of understand this wish for doing everything automatic, but it looks like people want more precise feedback, and these annotations they give them better feedback. So that's my impression now. Yeah.
I think there are 3 questions, so maybe we shouldn't hijack the discussion here. I guess I'm just going to read it out. Are there use cases for TLA+ which don't deal with concurrency or distributed systems? So I think perhaps another way of asking this question is, what kind of other specifications have you guys written that are not primarily about distributed systems, not primarily about concurrency?
I mean, if you think about smart contracts, for instance, it's arguable whether it's concurrent systems or not. I would say they're just sequential code, more or less, right? And you can write smart contracts in TLA+, of course, they're not. They look different from Solidity, for instance. But I wrote a couple of Solidity contracts in TLAPS to find some known bugs, right? And of course, there are these examples in the book, right? The Euclid algorithm can try to reason about sequential algorithms, right? I know how useful it is. Yeah.
Yeah, I think that's probably the follow-up to this question, right? How useful is it to write specify sequential algorithms in TLA+? So maybe to give another anecdote, so I've written once an algorithm in Pascal to generate the subsets of a set in a particular order to make TLC a little bit more efficient. So I found this algorithm in Knuth's The Art of Programming, but I wanted to familiarize myself better with the algorithm. And since because it was high stakes, I decided, okay, I'm going to write a Pascal algorithm for it. It took me half a day or so. And then it became more like using TLA+ and TLC as some sort of what perhaps people would call property testing, where I would define the input with the TLA+ operator, use TLA+ and the expressiveness of TLA+ to come up with this highly operator that defines all the inputs, and then I could simply run this on or check this on Knuth's algorithm that I adapted to look more like the Java code. Maybe the next other 2 questions here are for Stephan. How do the 3 backends, SMT, Xenon, and Isabelle, differ in behavior, and how should one go about deciding when to use any of them?
Yeah, so by default, these three backends are all called in sequence, right? We first call SMT, and if SMT fails, we call Xenon, and then we call Isabel. Because it's not always clear which one will win. So there are some cases where you can predict what's going to happen. So if arithmetic is involved, integer arithmetic, then basically only SMT will solve the problems. Xenon is good for problems that are essentially just first order logic, so formulas with a number of quantifiers. So quantifier handling is typically not so good in SMT solvers. And Isabel is the only one that can handle higher order proof obligations. So if you have, if you, for example, use a lemma that uses a higher order operator, something like p parenthesis something, and you want to instantiate that operator by something, by a concrete term in your specification, then only Isabel will be able to do that. Although we are now also experimenting with a more automatic prover for higher order logic called superposition, so that may at some point also show up in the distribution. And then the other question is about timeouts to the backends. So in my experience, it's usually not worth giving much higher timeouts. Occasionally, it happens that an SMT solver can find the proof, say, in 30 seconds that it cannot find in 5 seconds. But typically, that points to brittle proofs, and I would prefer decomposing the proof for a step. I mean, just one level deeper, and make the proof more robust, because you never know, the next version of your SMT solver may fail on such proof obligations.
Maybe a follow-up question. So with the model checking, obviously, with more compute is better, makes things faster. Is there going to be real improvement, assuming I have a 10 times bigger machine in terms of TLAPS? Would it make anything easier?
Hard to tell. So for one, I mean, I think nobody really has figured out how to decompose proofs on to make use of parallelism, right? Multi-cores or whatever. So I mean, basically all of the automatic theorem prover procedures today are still purely sequential. And so there's not much hope for, I mean, if you have a bigger machine, typically it has more parallelism, right? So that will not help you. And also, I don't think there's a good characterization of complexity. So I think what people just do is they run until timeout, and
And then maybe also a follow-up. What I wondered about is these pragmas, to what extent, or it seems to me it is as if the user has to know a lot about backend provers, their complexities, their strengths, their weaknesses. Do you see a chance to use, for example, machine learning to kind of create a model that could make predictions, have heuristics to guide the user in selecting, for example, backends?
Yeah, that's an interesting question. So, I mean, I think that there is room for using machine learning with theorem proving. So I don't know for recommending backends. I mean, I don't know if we have the data that would be necessary to train a network on that problem. There have been experiments with using machine learning internally, for example, figuring out what may be good instances, because that's one of the main problems that proof backends have. You have a quantifier, and you have a lot of terms lying around in your context, and which term should you instantiate your quantifier with? And I think that machine learning can make a difference there, at least if you have similar proof obligations that appear sufficiently often.
Then I guess I have one more question for TLAPS, but also for Apalache, and maybe this connects all of them again. So finding the inductive invariant is obviously super difficult. So what do we have to make this easier in the future?
I mean, what I have shown, I mean, I didn't talk much about it, but this approach of writing tests as you write actions, I think it's not a complete approach, but it gives you some room to think about parts of your inductive invariant without writing a complete inductive invariant. Basically, when you write an action, you have this context in your head, and if you try to write the tests, as I have shown you, right, I think you actually write some parts of your inductive invariant already. At least when I tried it this way, I thought, oh, actually, this is a test I would need for inductive invariant. It defines the shape of variables before an action is taken, and it defines the shape of the variables after the action has been taken. So I think there is some kind of unexplored space here, or maybe Stephan should correct me, maybe it's explored already. But I think there is some kind of methodology where you can try to reason about, a composition of formulas where each formula is defined for an action. Because usually you write an inductive invariant over next, and it's hard. It's just hard because it's a large transition system. But if you think about individual actions, you can already harvest a lot of useful facts about your to-be invariant, right? So I think we should really look at it and just experiment with specs. Maybe we'll find something like.
Yeah, in order to just as an add-on, I think there has been actually work on generating invariants. I mean, using symbolic model checking techniques and so on for generating invariants for embedded systems, IC3 and so on. Yeah, I think. I mean, there is definitely work on this topic, on how to extend that to distributed algorithms, and I think that is super interesting work that we could benefit from.
I mean, there's also this, I would say, this human ingenuity part to it, to finding the inductive invariant, right? So to what extent do you think we need tools to lift the problem out of the mathematical formula into the application layer or problem domain layer for humans to better inspect? So, for example, talking about this animator modular that we have, or these various other visualizations from which I think, at least I as a human, get a lot of insight from. Do you think this is worthwhile to look into this more, or is it or it's unsuitable because it doesn't really scale to big enough problems? What are your thoughts about that one?
I mean, I know I'm a bit skeptical about all kind of animations and visualizations. I also tried them a long time ago when I played with model checkers, and yes, they do help for small specifications, as you say. But the moment you have large graphs, I think they don't give you any intuition. That's a problem. We have these hairballs, right, as we have seen in different talks. They're just lost there immediately. Yeah, I think we should extract the knowledge from the engineers or whoever the specification writers. They have this knowledge. The question is how to do it, right? And somehow what I have got from working with engineers is that they're often willing to help. This idea about the push button approach, it's very nice, but we are not using the knowledge of the people who are writing the specifications. So these people are willing to help. We just have to find the proper interface to them, right? So that's why I'm saying we need some kind of this compositional approach, or maybe help them to think about smaller problems. Animations, I don't know. I think giving examples, that's a way actually to help engineers. If you give an example.
Yeah, I think so too. So
yeah.
when I think about how you come up with an inductive invariant in the proof, and you start with the property that you're interested in, and then you try to prove that it is preserved, right? And you find, well, that proof doesn't work, and then you think about, well, what am I missing here, right? And so maybe if we had a tool, you know, that could help us with counterexample construction there, and that could show us, well, look, your obligation fails because here's a counterexample, here is a pre-state and a post-state, and you have failure for your invariant preservation. That could point to, then a human could say, oh yeah, sure, but that cannot happen because blah, blah, blah. And then you strengthen your invariant.
Yeah, I mean, that's to some extent what we're doing in Apalache when we prove inductive invariance, right? A problem as I have seen myself is that if you try to prove inductive invariant over the state of the transition relation, right? You get a counterexample and you have no idea what's going on, right? You just have a bunch of states and you just don't know what's going on, right? That's why I think it actually makes sense to talk about individual actions, because in the context
absolutely.
of
So
one
I mean,
action,
that's what we do in the proofs all the time, right? The first step is you break down your next state relation, and then you look at the proof action by action. Yeah.
Yes.
Because otherwise, it's just too big. You don't know what's going on.
Yeah. But examples is definitely something that people understand. And even, I mean, when I'm writing myself the specifications, I also need examples. So I think I have a couple of questions there.
Yeah, maybe the last one first.
They want to.
Okay, still with TLAPS.
Let's continue with TLAPS, and then I can talk about the debugger. Okay.
Yeah, improving space-time complexity. So that is not something that we are looking at, and I don't think we'll have the manpower. I mean, there are other proof assistants. That's a topic that other proof assistants are interested in, right? So there's work in Isabelle and there's work in Coq on such things for sequential programs, to my knowledge. Well, you have to do a lot of encoding, and you have to develop the libraries to do that, and I think it's not on our list of priorities. So if you're interested in improving time-space complexity, I would advise you to look elsewhere. You'll probably get a usable result earlier.
Speaking of libraries, by the way, I mean, we do have these community modules now for general constant level operators. Do you also have plans to kind of crowdsource the TLAPS theorems and grow the repository or the set of theorems that way? Is it possible for people to contribute new theorems?
Of course. So we don't have. So at the moment we don't have any standardized way for doing that, right? So. But yeah, of course, I mean, it's when you write your own proofs that you see what's missing from the library. And so far it's been mostly myself and a few others who wrote the lemmas, and this is not going to scale. So yeah, absolutely, we need contributions, and we need a way of getting people involved and making them, I mean, giving them also the credit for the contributions they made.
Okay, I guess then I can take this question on about the TLC debugger and the REPL, whether or not they're going to be included in the stable TLA Plus toolbox release. So I think this has a bigger perspective, this question. First of all, I would like to have, or we would like to have more frequent TLA tools releases. I think Apalache releases monthly, bi-weekly?
Weekly.
Weekly. And with the toolbox, the problem is pretty much that it requires a lot of manual testing, at least a lot of manual smoke testing, because it's a graphical front, and you have to make sure that it works with the latest version of Windows, and then Mac OS comes along and changes something. It's just a lot of manual labor, engineering labor, that makes me refrain from releasing too often. And I wonder if it makes sense to decouple the toolbox from TLC. Right now, I would say there's more work going on in TLC. And then it overall kind of asks the question, what about the toolbox and the VS Code extension? What's the roadmap here long term? Right now, the toolbox is way ahead in terms of features, but it seems to me that especially among new users, and they are primarily engineers, they just find the VS Code extension more appealing, looks more modern. I see it like a pendulum, right? Last decade, IDEs were on vogue. This decade, you have lightweight editors where you plug in all features later. Maybe next decade it's the other way around again. I don't know. But this decade we definitely want to focus on the VS Code extension, not just because it's lightweight, but also, for example, because it runs on the web. And I find this idea of having this web IDE that has zero install very appealing, and also has a massive amount of compute available. So I don't drain my battery if I do model checking. Let it be with Apalache, let it be with TLC. Yesterday or the day before yesterday, I tried to install TLAPS on my ARM64 MacBook. It doesn't work, right? Because there's some library, PolyML pure, part of Isabelle, that doesn't compile. And it takes me 3 hours to figure this out, whereas in a web environment, this would all just disappear from the user's perspective. One of us would have to figure this out, obviously, for the web, but then we have a defined environment. So I think this is really attractive. And we obviously don't want to make it so that it depends on Azure, for example. Yeah, it should be independent of Microsoft, should be independent of any cloud provider. But then it would be, I think, would be really nice. So obviously we want to invest in the VS Code extension, and this connects them back to the question. This TLA Plus debugger that I built for TLA for TLC or for TLA Plus, that's only available in the VS Code extension. So that's the only feature that the VS Code extension has that the toolbox doesn't have. This was initially for technical reasons, because it uses a certain framework that doesn't exist in it, at least where there's out-of-the-box support in the VS Code extension. But it could also be added to the toolbox. It's just a matter of engineering work. With a debugger, I'm fundamentally not yet sure how useful this is going to be. I've been using it a little bit, as much as I can. I really like to use this on a new specification, a novel specification that I write, to see if I gain any kind of insights. And if somebody else has done this already, then I would be happy to get feedback. Because we also have this counterexample, right? We get these traces, and there's a lot to learn from traces, and I don't want people to get stuck inside a debugger. And I mean, if I just think about the time that when I program, I waste on debugging things instead of thinking about things, I don't want to encourage it. But maybe it's useful. So I have this short recording that where I use. Well, on every save, I simulate the specification with TLC for depth 100 and 10 behaviors or so. And if it finds an error, it runs in debug mode. So if there is a spec bug, like what you would find with type check in Apalache, the debugger immediately pops up and shows the location of the error, underlines the line of code or the line of the spec. You get to see the outline, you get to see the trace and everything. It seems to be super useful. I mean, it's just proof of concept thing right now. But I'd like to invest that investigate that more. Yeah, and then shifting over to the REPL. I mean, Will here, I think he's also in the call, contributed this REPL, and people really seem to like it. We're always a little bit suspicious about a REPL or reluctant to add a REPL historically, because we thought, okay, we have this evaluate constant expressions. But yeah, it seems even though it's limited to constant level expressions, the REPL, people really like it. What's missing right now is, I think, nice syntax highlighting. If somebody knows how to do that, please contribute. And then, yeah, it goes back to putting out a TLA+ toolbox tools release that includes the REPL. I mean, it's part of it already. Somebody wants to add a couple of commands to the REPL. I don't know what the state of that is. It's usable, it works, it seems to have value. It's more integrated into the VS Code extension. I have a button to open the REPL. Yeah, so stay tuned. My personal deadline is end of the year to have a new toolbox release, to just give you a short version of this answer.
Actually, I have found REPL quite useful, especially when explaining, new people, beginners, why certain TL expressions are not doing what they think they're doing. That's extremely useful.
Yeah. So I've even tried to take it to the next level, so that we can kind of deal with the temporal part, at least kind of in a hacked way with the REPL. So I have a bunch of operators, or the TLC now has a bunch of operators with which you can do I/O and spawn processes. So inside of the REPL, I can spawn a nested TLC that does some model checking, and then you get the result back. And ideally, that's still on my to-do list, you get the trace back, right? So then you can put this trace into a variable in the REPL, and from there analyze the trace again, and perhaps do this multiple times for various sets of constant values, and then compare the traces with each other. Would still be constant level formulas though, but so the trace becomes a record or a sequence of records. But that seems to be, that I find interesting. With Apalache, you obviously have this nice constant init feature where you can check various constant values, kind of first class, but TLC cannot do that easily.
Yeah, actually, maybe I should have this question. I have been thinking about it for some time. The problem that I see with all these three tools is that we have a lot of smart algorithms inside these tools, and it's kind of hard to explain how they work. I guess TLC is relatively easy to explain intuitively, at least, right? The Apalache, it's harder, that's why I wanted to explain it a bit. And TLAPS, I don't know, maybe you need some training even to understand how they actually work internally. Do you think it would be possible to somehow minimize the core of every tool, to make it as simple as possible and keep it at the understandable level, and then all the other things, all the complicated algorithms, to turn them into something, scripts or something like that, that people could just analyze the scripts and say, I see how it's working. The core is complicated, but it's small, so I trust it. But say the way TLC does liveness checking, for instance, he's an algorithm, right? Do you think it would be even possible to do something like that?
Stephan, do you have an opinion?
Well, I mean, the algorithm that the TLC uses is pretty known, right? So to what extent can you explain that to a user?
Yeah, but I mean, TLC internally is actually doing a lot of things, right? The algorithm itself, I can explain it in a minute, right? If we're talking about breadth first search. But there is a lot of magic, at least I have this impression that there is a lot of magic in TLC.
I think, to me, this has two dimensions. What you want to accomplish expects a certain level of expertise from your users. And I think the main users of Apalache right now are perhaps a little bit more, I wouldn't say sophisticated, but perhaps are better trained in terms of formal methods, have more background, deeper background than, for example, distributed systems engineers who just see TLA+ as yet another tool as part of a tool belt. So they really just want to have this push button thing and get a thumbs up or thumbs down kind of result. So whatever we build is ideally kind of scales, right, from both ends. If I just give a distributed systems engineer a script and here, go figure it out, the algorithm is kind of simple enough, then I don't think it will attract a lot of people from industry. I think it would make it a little bit harder. I just get this, for example, I get this feedback from using the VS Code extension. Now people have to deal with TLC's config file, and it turns out people really fundamentally like this model editor that the toolbox has, because it's just a bunch of knobs and buttons that you can click, and they have nice labels that explain pretty much what they do. But that's not to say that the other kind of user mode is invalid. And I think traditionally, maybe we have put too much emphasis on the toolbox and hiding everything behind the toolbox, making everything else more difficult to accomplish. Also maybe because TLA+ as a language is kind of isolated from everything else, right? You just have your model, you have a specification, it's math, there's no connection to Rust or Haskell. But it would be nice if the tools at least would be more open to interface with outside ecosystems, with other ecosystems, programming languages, and so on. And that's part of what I've been trying to do in recent couple of months, to build integrations that are easily maintainable and yet powerful. And then coming back to TLC, I think what makes it a bit difficult, I mean, this liveness checking, I would say it's probably the most complicated part of TLC. It's not just a textbook algorithm, it's an extension of it to handle the actions. So that's difficult to get into. But then obviously, I mean, it's 20 years old, the code base, and it has been extended by multiple people. It's not the most elegant piece of software engineering, not just because there were multiple people who worked on it, but also because it's supposed to be super fast, right? There are all these optimizations that make the code more difficult to read and understand. Yeah. I don't know if you can break anything out of TLC. Usually, because of these optimizations, everything is tightly coupled. It makes it difficult to isolate parts of it. But as you say, at its core, the safety checking is just breadth first search, right? And it would be nice for somebody to eventually implement depth first search, real depth first search, right? Not iterative deepening. On the other hand, I don't know how much. I don't want to add too many features to TLC, because every feature means it has to be maintained, because there's this one user that's going to cry bloody murder if we remove this feature.
So we've been talking a lot about internal stuff, right? I mean, given a specification, what can we do with it? How can we verify it, and so on? But you just mentioned, and that's something that I actually wanted to bring up. I mean, at the end of the day, systems are not implemented in TLA+. So how do you make this transition? Is there any, I mean, you must see that, right? And your work with distributed systems people. So what is the value that they get out of a specification when at the end of the day, they have to build an implementation?
Yeah. I mean, in practice, we actually have two kinds of specifications. One in TLA, and another one is the mixture of English and mathematics, basically, more or less like POTC style, POTC disk style, right? It's hard to say that people, I don't think that people would say they prefer the TLA specification to the English one. It just, that wouldn't be true if I say that, okay? But they see the value the moment you can generate tests for them. And that's what we're actually doing. So when we have specifications and we're generating, for instance, unit tests or sometimes integration tests, people immediately see value in that. And that helps actually to engineers to understand what specifications is describing, what kind of level of abstraction is describing. What I actually have found interesting in this activity is that not only you refine the implementations by TLA specs, it often happens that you find bugs in the TLA specifications by running tests. And that's very interesting. I think there is really a lot of space here for this interplay, because when you write the specification, sorry, when you write the specification, you can just miss something. And if engineers have thought about it, they might find problems in your specification. Yeah. So, but I think it's really they see value in something that is running, which is very natural for engineers, I think.
Yeah. I mean, it so happens, and that's why I have to leave in a couple of minutes. I train people at Microsoft, engineers at Microsoft, and right now I'm training people from a team who's embraced TLAPS before. So the team has seen the value of it, and then it becomes a lot easier to sell to the engineers because they really use it as a design time tool. So before they write code, they use TLAPS to find out if the reasoning is correct about a complex system, and they like it very much, right? And then once they figure out, okay, so this algorithm, this system, this design of a system could work, then they use different tools to implement the system and make sure that the system conforms to its specification. Last week at the TLAPS conference, for example, the keynote speaker from CrowdStrike said, okay, we don't have a technical integration, a formal integration between our specification and our implementation. We just have a process that guarantees that if you change B, you also have to change A, or at least give an argument why you don't change A, the spec that is. That already covers 80% of the problems for us, right? And yeah, I think, or I realized that most new people to TLAPS are not very satisfied with this answer. It's not so important to have a formal connection between the code and the spec. And I think what Igor has, or whatever the formal system has with the model test case generation, that's quite nice. We also heard elsewhere that it would be nice to do the other way around, where you do conformance monitoring, and this is all possible. It's a lot of engineering work, I would say, to get this set up. And usually you do just for one ecosystem, just for one programming language runtime, programming language. That's a lot of work. So we will have to crowdsource that part. But yeah, fundamentally, I think just thinking about the algorithm with TLAPS is super beneficial, and it's underappreciated in the programming language community to just think either in Word documents or with a little bit more formal math in terms of TLAPS.
It's definitely useful, right? Just I think the main problem is that if you specify your protocol in TLAPS, say if I specify the protocol in TLAPS, and they expect 10 or 20 engineers to read it, they should see a value in what they do, right? Just, it's hard to tell them, look, it's TLAPS, it's all formal and nice, go and read it. I would say, yeah, maybe I just look at the implementation. It's like easier for me to read. But if you tell them that they can extract some value out of it, produce examples, counter examples, they would start to see this value. Right?
Okay, I have to leave now. So thanks everybody. Thanks for the discussion. Thanks for the question. But please continue. Bye-bye. See you next time.
Thanks.
Bye-bye.
Thank you a lot, Markus. Thanks.
So I don't know, do you have any
I don't see any
questions?
new questions in the chat.
I'm not sure I have answered this question about when one should choose Apalache over TLC or vice versa.
All right.
Yeah. I mean, this is very hard to answer, actually. I can say that in formal systems, when working now, we use both model checkers. And since TLC is much more mature and you have the toolbox, right, it's just easier to start with TLC. But sometimes you just hit the wall. If you're talking about clock synchronization, in my example, or you want to explore some kind of protocols, for instance, smart contracts, right? Again, smart contracts, where you transfer some coins. Especially if you want to generate tests, Apalache becomes useful because sometimes you want to generate tests that talk about millions of coins. For instance, you want to find an overflow, right? It would be very hard to produce examples with TLC where you have very large integers. It basically would have to manually, tune your domain to produce very large integers and just a few of them. Apalache would do it very easily just because the SMT solver would solve constraints of arithmetic, integer arithmetic, for instance. So yeah, sometimes you just see that you need large domains, and again, you have these bounded data structures, but for instance, you have integers. In this case, you can try Apalache. If you have combinatorial puzzles, for instance, any kind of, small combinatorial problems, TLC would definitely win them because the solvers would have hard time solving these combinatorial problems. And TLC will just enumerate all values in several seconds, I think. Yeah. So I just want to say that at some point we thought maybe Apalache would be a drop-in replacement for TLC, and people asked about it several times. But then we realized it's probably not true. Like, you cannot say that one model checker is a replacement for another one. They have different capabilities and strong and weak points.
Yeah, that's also my experience so far, right? I haven't used Apalache very extensively, but sometimes it's been really good. I mean, really useful. So in particular for checking inductive invariance, of course.
Yeah, I think we should explore this and see how we can efficiently use Apalache to check inductive invariance. We actually used it again to check safety of tendermint consensus, for instance. But it's a relatively large algorithm, actually. And I think it took Apalache maybe a day to check the inductive invariance for 4 to 7 processes. And so not huge numbers. But I could just leave the machine running and let it crunch the numbers, let the solver do the job, right? I think it would be good to have a proof in TLAPS, for instance, but it would take much more time.
Of course.
So it's always this balance between how much time you have and how much time you want to invest.
Yeah.
Yeah, I don't know if there are no further questions. Probably we should close the session, and it's very nice.
Yeah.
Talk about 3 tools, not just 1 tool.
Yeah, but still, I mean, they are integrated, right? I mean, that may be something that we should have stressed a bit more. I mean, I don't actually know of any other theorem prover, for example, where you can just fire up a model checker and verify your theorem for a small instance, and that gives you a lot of confidence.
That's true. I don't think there is anything like that, actually. It's true. It's true. And I think it's also a good backup for you if you do model checking. You know that if it's really important for you, you can go into TLAPS proofs. That's also a good thing in the back of your head, right? Yeah.
Okay, so thanks a lot to everybody, right, for attending. It's been a long afternoon. And yeah, see you someplace, somewhere, hopefully physical.
Okay. We can go to Frida now. Yeah, see you around.
See you, bye-bye.
Bye-bye.